Okay. Hello, everybody. Can we gather around? We're about to ready to start our session. Yay! That's a photon.
Hey, Gordon, we did it.
Exactly. We're still here. Okay, we have a very exciting science and technology session this morning. First of all, I want to say thank you all for coming. It is wonderful to see so many familiar faces get back together and enjoy this very exciting moment, the inauguration of the Fred Young Submillimeter Telescope. Thank you very much to Fred for all you've done for so many years. So I should introduce myself to people that don't know me. I'm Gordon Stacy. Oh. And I'm a professor at Cornell, have been for a long time. I calculated more than half my life now. And I'm the project director. And Martha is the chairman of the board of directors. And today, I want to first do some logistics. Don't drink coffee because you haven't been tested yet for your blood pressure. I can tell you from personal experience, even if you haven't drunk coffee, you can fail. And on the back, this is your magic card. And on the back of the card, in the lower left, is the appointment for your test. Your test is just a blood pressure test, and they test your oxygen in your blood as well. And if you fail the first couple times, they'll let you relax for a bit, and hopefully you'll pull through, and then you'll have another chance tomorrow if you don't pull through. So I'm crossing my fingers. I haven't drunk any coffee in a long time now, so I'm going slower than normal, but that's good. Let me see. And then over here is what bus you're going to be taking tomorrow when we go up. Let me see. And Jim will tell us a lot more about that. Jim is in there's Jim in the back. So Jim is the Grand Master and has pulled us through the time to this great event. Okay, so I think I'm ready to go. We're ready to go. The first speaker is Professor Martha Haynes.
Okay, so thank you very much, Gordon. So we start today talking a little bit about the history of this project. That's my part. And in order to do that, the first thing I really have to do is start saying thank you to a lot of people. So I want to do that because that's an important part. We wouldn't be here if it weren't for a very large number of people, many of whom are here, but a lot of whom are not here, and also the people who have provided the funding. So I just have the list here. I'm not going to go through the list, except to say that, of course, Fred has been involved, but also a lot of the universities. We're an academic consortium, not a big multinational collaboration or an agency, single agency sponsored collaboration. It's different. So we go out and have gotten our funding from universities, Cornell, from universities and the German Science Foundation and the Max Planck Institute for Astrophysics, from the Canadian Foundation for Innovation, and the universities of Waterloo, Toronto, Alberta, British Columbia, and the provinces of Ontario, Alberta, and British Columbia, and also from our newest partner, Duke University. And without that support, we wouldn't be here, so we have to say thank you. Seriously, thank you. We also wouldn't be here if it weren't for the fact that the Chilean country is very welcoming to astronomical facilities, of which we are perhaps the latest. And I think we have to recognize the great assistance and infrastructure support that Chile provides us, both allowing us to operate through the University of Chile and the Ministry of Foreign Affairs, being part of the Parque the Atacama Astronomical Park under the auspices of ANID. We have an agreement with the Chilean Time Allocation Committee so that Chilean astronomers are able to participate in our project in the same way that astronomers at our own partner institutions do. And we, in return, have invited the Chileans to participate in our the oversight of our corporation and our science planning. So thank you to all of Chile for making it possible for astronomers like us from all over the world to come here and realize our dream of building a telescope. I also need to mention we have a lot of friends who are our neighbors here, so to speak. And they are the other facilities that are located in the same area with whom we collaborate or exchange ideas, infrastructure, and services, including the ALMA Observatory, which we will be visiting tomorrow, who will host us at the inauguration ceremony, the Tokyo Atacama Observatory, who lie even higher than we are, and we'll see their telescope from afar tomorrow, APAC and the Max Planck Institute for Radio Astronomy, the Simons Observatory, and Radio Sky, who provides us access to infrastructure services. I also want to thank personally my friends from the Associated Universities Incorporated and the U.S. National Radio Astronomy Observatory, who were especially helpful in the early days and helping us get access to the land, and also many adventures of traveling around looking for telescope sites. So thanks to all of them. Having good neighbors is really a great thing, and there's only one universe, so having all these other astronomical facilities work with us helps a lot. So thanks to them. And the last group of people we have to thank are all of the people who've been working up at 5,600 meters on this telescope. I think it's been amazing for me to watch them on our security webcams, watching them climbing up when there's snow on the ground. You know, we're used to snow in Ithaca, New York. It snows there all the time. It snowed there Sunday night. But watching these people working up on putting the telescope together is really inspirational. And so I want to especially give thanks to the CCAT staff here in Chile, Horatio, David, Oriel, Diego, Roberto, Evelyn, and Pedro, who've made it possible. You are members of the CCAT family, even though we don't know you very well. And we thank you for all your efforts. So I thought I'd just give a little overview, and then you'll be hearing the rest of the day about all the details. So what is FYST anyway? And it is pronounced feast, because in English, a feast is a big gathering of people where they eat a lot and have a good time. And so FYST is supposed to gather a lot of astronomical data, and we're going to have a good time. It is called the Fred Young Submillimeter Telescope. Here's a picture of it taken in Germany 2 years ago. It's a 6-meter diameter dish antenna, and it's kind of a weird, it's probably not what many of you think of as what a telescope should look like. But hopefully you'll see it, and you'll realize that it has 2 mirrors in it, and we'll hear more about that later. It has a novel telescope design, which largely we can attribute to my young colleague, Mike Niemack, for coming up with the idea of building this telescope. And it's been constructed by CPI Vertex and Tenon Technique. It will scan the sky rapidly rather than looking at making exquisite images of small areas of sky. It will look over large areas of sky. And we like to say, although Tau is a little higher than this, they're only about 100 feet higher. It's the highest observatory to which you can drive a truck, which means that we'll be able to take advantage of improvements in technology over the next years. We don't have to wait for the next space mission. We can just drive a truck there. And we'll also hear later on that it will do coordinated legacy surveys. It's not a type of thing that an individual astronomer goes for observe for a few hours. We do big surveys that are well coordinated and thought out. Why is submillimeter astronomy? I'm going to leave this mainly to Frank Bertoldi to explain to you. But basically, we observe a different part of the electromagnetic spectrum, the light spectrum. Not the kind of light that our eyes are sensitive to, but a kind that our eyes are not sensitive to. And I just point out that if you look with standard night vision, or you look with infrared emission, infrared goggles, you get a different picture of the universe. And that's the point. We're getting a different view of the universe. We're seeing objects that other telescopes don't see. And unfortunately, submillimeter waves are blocked out by the water vapor in our atmosphere. So you have to be really high and really dry, or else you have to go to space. But space missions are much more expensive than a group like us could possibly afford. And we can drive a truck to our observatory. So here's, again, a little schematic of the telescope, and you can see, if you look carefully in the image on the right, which was just taken a week or so ago, there are two mirrors, one lying at an angle and one almost vertical, and that is what makes our telescope special, and Steve will tell us about that. So who is Fred Young? Who is this guy? Fred is my very dear friend. I hope he knows that. And Fred is a businessman. He's been very successful. But he also has a real passion for understanding the universe. And he has taken his passion and helped us to build this telescope to explore the universe. He's been with us. He first traveled with Riccardo Giovanelli in 2002 to Chile, looking around at observatories, and then I think the next year you went actually to travel to this area and climbed up part of Cerro Negro. That's a picture of you. I hope you remember that. But Fred has also come to a lot of our meetings. So you can see in the picture on the lower left, Fred is participated in one of the design reviews when we were for the concept design for the telescope, which led to the awarding of the contract with Vertex. So who is CCAT? In order to run a telescope, you actually have to set up an organization. It has to be able to have bank accounts and access to land and human resources and all that. So it is a not-for-profit corporation established in the United States. It has partners, which are Cornell University is the lead partner, a German consortium, including the universities of Cologne and Bonn and the Max Planck Institute for Astrophysics, the Canadian Atacama Telescope Corporation, and which itself is a consortium of 8 Canadian universities, and of course Chile as the host country. And it took us 3 years to set up this corporation because the legal stuff is complicated, but we did it. We figured out how we could work together, and we do work together very well, I think. Why in Chile? Chile has a long history of hosting astronomical facilities. There are a large number of astronomical observatories. We, of course, are located adjacent to the Atacama Large Millimeter Array, which is what makes it possible for us to sort of piggyback on the infrastructure development that they have done here in the San Pedro area. And we operate under what's called the astronomy law canonically. And it allows us to operate as a foreign organization building a facility in the country of Chile with access to land that is protected for astronomical and scientific use. So just a little bit of history because for me it's very personal. It goes back in 1994, that was before ALMA. And ALMA, astronomers around the world were thinking of building a millimeter array, slightly longer wavelengths than we will do with FYST. And Riccardo Giovanelli went with people from the US National Radio Observatory to scout out sites in the northern Chilean, the region around here. They spent a lot of time actually further north than San Pedro, to the northeast of Calama, but they also came to this region at that time. At Cornell, we had a group that did radio astronomy and ran the observatory in Arecibo in Puerto Rico. And we also had people who did far infrared astronomy using space telescopes. And this group of people got together and said, Ricardo said, they're probably going to build this array on this plateau. But the plateau's only at 5,000 meters. And there are peaks that go up to 5,600 meters. Wouldn't it be fantastic to build a far infrared submillimeter telescope at a higher location? And so my colleagues at Cornell started thinking. At the same time that the US National Radio Astronomy Observatory was thinking about ALMA, the European Southern Observatory and the National Astronomical Observatory of Japan were also thinking about building millimeter arrays in the area, and they got together, and since there is only one universe, they said, we shouldn't build 3 arrays, we should build one bigger one that's bigger than any of the 3 individual ones we would build, and so we ended up with ALMA. And as I said, we'll visit ALMA tomorrow. It consists of 54 12-meter antennas and 12 7-meter dishes set out on this extensive broad plateau at 5,000 meters elevation, and it is truly a global partnership. It operates principally at millimeter wavelengths. They can do some submillimeter astronomy, but they're lower down, so fewer of the waves get through the Earth's atmosphere. We are higher up. They make exquisite, detailed images of tiny patches of the sky. But in order to study those patches, you have to know where to look. We will be the wide-angle telescope that will survey large areas of the sky and discover things that then people will want to go look at, follow up with using ALMA. Just a little bit of history again, because this is personal. You'll recognize in this photograph, perhaps, Eduardo Hardy, although he doesn't have the same tie on. And this person in the green with the brown hair, that is me. This is at the ceremony where the then president of Chile, Eduardo Frei, signed a decree conceding this area of land for scientific purposes. Again, I said that Chile has been very helpful, visionary perhaps, supportive of science in a general way by setting aside and making access of this exceptional area for astronomical facilities. So beginning in 1997, the CCAT team started carrying out observations. We had to figure out, where are we actually going to build a site? We want to be higher than ALMA. So we started doing site testing, in particular on this small hill called Cerro Chico, which I don't think is actually an official name. It's just a little bit of a hill, so we called it Chico. And that was one where my understanding is that the way the tract was bulldozed to the hill was there was somebody there with a bulldozer that my husband, Ricardo Giovanelli, met on a plane, and Ricardo convinced him that he would give this person a box of foot warmers if he would bulldoze the track up to Cerro Chico. So that's how it happened, and we started working on Cerro Chico. And so here are just some pictures of people in the good old days working on Cerro Chico just to try and see, is this site going to be a good site for submillimeter astronomy, and what is the transparency and stability in particular of the atmosphere? And so they launched weather balloons, they made observations, and it was kind of the Wild West. In 2005, Ricardo hiked with 4 Chileans up to Cerro Chajnantor, and within a year, we had actually been able to drive up enough with a container to set up the site testing materials, and by 2009, it was clear that this was just an exceptional site for submillimeter astronomy. So after that, between about 2017 and 1997 to 2016, I'm not going to go through all the details, but in those years, we developed the project scope, set up the site selection, the partnership, the organization, the legal formulations. It took a long time to do that, but it's kind of boring, so I'm going to skip it. Things got really exciting in the period from 2017 to 2020. You see on the left the telescope that we thought we might build. You'll see the telescope sort of looks like that, but not exactly. And here's just a picture of the site taken on December 2nd, 2020, which is the day that they actually started to level, blast for the foundation of the telescope. So over the last few years, from 2021 to 2014, that's when we set up the fabrication and pre-assembly of the telescope in Germany. You don't want to do work too much at 5,600 meters, so instead you build your telescope in Germany, put it together, then take it apart, ship it, and deliver it to the top of the mountain, and that's what happened. In synergy collaboration with the Tokyo Arakama Observatory, they constructed the road, although it was based on an original design with some modifications that we had undertaken. In return, we have built the power station and done the trenching and the cabling. Here are just a few pictures showing you how the site has been transformed. Here in 2021, you can see on the left-hand side above the earth-moving equipment, there's a hole for the foundation. By November 2022, you see the foundation of the telescope and some containers being put in there so work can start. And here we are on the 28th of March 2025, where the telescope has just arrived in Chile in pieces and is about to be trucked up the mountain. And this, again, is just to show you that there was a lot of other stuff that had to be done besides putting the telescope together. Putting in the foundation, it's not easy to pour concrete at 5,600 meters. How do you do that? Well, we did it, apparently. There was the trenching for the optical fiber and the power cables, and the construction of the power plant. So then we get to the exciting time, which is the last year or so, where the telescope was transported to Chile and reassembled at the summit. And so now you see the picture taken on March 30th. Sorry, I had to turn my slides in and didn't get to update it, but you're going to see it for real, so what's the point? Besides, they've done more on the telescope since I left North America. So I just want to say it's been an exciting time. This is really, really an amazing time. We've gone from what was a dream, just a thought by a group of people. We've collected a collaboration and gone from a schematic CAD diagram to an actual telescope. And so I want to end just by saying, he would say, Fred, now he would say, we built the sucker.
Thank you, Martha, for that wonderful and emotional talk. We all miss Ricardo. He started it all. Next speaker is Frank Bertoldi from the University of Bonn, a longtime colleague. We intersected when I was a postdoc at Berkeley.
That's right, yes. Indeed, very emotional moment here. Yeah, I'm Frank Bertoldi from Bonn, and I'm trying to give you a bit of a context. Why we built the telescope up there. Martha mentioned it, I'll pick up from that. And what it is, like what wavelength range we're focusing on, and why that is, oh, that's important, yes. Why that is interesting to us. And but before that, sort of more thought, science, I always get very emotional about coming here to Chile. It's such a beautiful place, particularly the Atacama Desert, and with its wonderful, friendly people, with the really astonishing landscape, with the and the beautiful sky, of course. Here's a picture of the night sky taken from this Chajnantor plateau. And you can see a number of interesting things. San Pedro de Atacama on the right, bright spot here. The Milky Way, which is, I always find amazing, it's so much more beautiful than in the northern hemisphere, what we used to. And you can see even two galaxies, our neighboring galaxies, you only can see from the southern hemisphere, the Magellanic Clouds here and here. There are only three galaxies that you can see with your eyes, with your naked eyes. The Andromeda Galaxy in the northern hemisphere is the other one, and the Milky Way, of course. You see this band of Milky Way, which is so much more spectacular from the southern hemisphere than from the northern, including a view into the galactic center, where the bright spot is there, where there's a massive black hole hiding behind it. So I want to put this a bit in the general astronomical context, why we're looking at submillimeter astronomy, particularly to those who are not submillimeter astronomers. So forgive me, my colleagues, for being a bit broader in this way, and you're going to have more expert orientation on the subjects that we're investigating this afternoon from my colleagues, and this just sort of starting with the obvious, with the visible, and I think that's very beautiful. What we see here in particular, you can see the Milky Way, but all these dark patches in there. The Milky Way, this milky haze there that you see in the sky, it's all stars. A galaxy contains something like 200 billion stars, and most of them are very distant. Actually, we can't look very far into our disk. We are in the disk of our Milky Way galaxy, sort of a planar disk, and much of that disk is obscured by dark clouds that you can see here as these dark patches. Actually, they're much more spectacular also here in the southern sphere. So take an opportunity to go out at night and adopt your eyes for 15 minutes to the darkness and then look up in the sky. It's just amazing. And you can see these dark patches and the Magellanic Clouds. And these dark patches, they're in the optical, of course, they're a nuisance because they don't let us look deep into our Milky Way galaxy. But these are the big clouds, dusty clouds, where stars are born, where they're formed. And if we go to different wavelengths, we can actually see young stars being born into them, but we can't see it in the optical. That's why we need to also go to other wavelengths. What else do we see in here? There's, most of the stars are in this galactic plane, but there's also a uniform distribution of stars. They're more nearby. That's those 6,000 or so stars that we can see with our naked eye. And of course, what we don't see except for these three galaxies are billions and billions, actually billions of galaxies outside of our Milky Way that you need telescopes for, or at least binoculars. You can start seeing these galaxies. And it's these, we estimate there are, in our visible universe, there are about something like 2 trillion galaxies in our universe. And we may be able to see maybe a few hundred billion of those galaxies if we look deep enough with our most powerful telescopes. And astrophysics is about understanding the structure and the time evolution of these galaxies. And we can look back in time. We can actually see the entire universe through its whole evolution from the Big Bang to today in this sky. Of course, not at visible wavelengths, which are aesthetically very beautiful, but we have to go to other wavelengths. And let me put that in context. Oh, here, by the way, this is, if we put the entire sky in the optical, we call that the visible wavelengths. That's where our eyes are sensitive. On the plane, you can see here, this is the part that we can see from the southern sky. And on the left, that's what we see mostly from the northern sky. And here's my point. It's much more spectacular in the southern sky. And then down there are the two Magellanic Clouds. We're more familiar with this kind of projection of a sphere onto a plane. So, and if we put the galactic plane, the Milky Way, in the center plane, that's how we usually display astronomical maps. You can see all these dark patches, and when zoom in, is the galactic center, these clouds that are obscuring in the optical, but are interesting scientifically in their own. And there are actually subjects of submillimeter astronomy in particular, because we can look deep into these clouds and follow how stars form. If we had different eyes, you know, this is the optical, this was the optical. This is gamma rays. These are the sort of most energetic photons in the universe. And they come from very energetic processes in the universe I don't want to get into. And they are not obscured by these dusty clouds. That's what the Milky Way would look like in gamma rays, if we had gamma ray eyes. In fact, every wavelength we look at, the sky looks different, and we see different kind of phenomena. This is the sky as it would look like in the radio, the very long wavelengths, like 40 centimeter, 50 or 80 centimeter wavelengths, radio wavelength. We see lots of energetic electrons emitting, energized by supernova remnants, very hot gas here. And in fact, if we just focus into this galactic plane and line up all sorts of surveys at different wavelengths that astronomers have conducted, you see how different the sky looks like, particularly the Milky Way looks like a different wavelength, from the radio on top where we see energetic electrons, then the atomic hydrogen has a very prominent emission line at 21 centimeter wavelength. Then carbon monoxide, our favorite molecule, that traces the dense gas that we saw earlier in these dark clouds. Then the infrared, where we can look deep into the Milky Way. We can see these dark clouds actually in emission. We can see where stars are forming and lighting up the surrounding dusty clouds. We can't look at optical wavelengths into them, but in the infrared. And then in the optical here, that's what you saw earlier, X-rays, hard radiation, similarly obscured by dark clouds, and the gamma rays, again, rather unobscured. So every wavelength you look at, you see the universe in a different way, and there's different information on the structure and what's happening in there. And if you look off the plane deeply, like this famous Hubble Space Telescope optical image, and that's a small patch in the sky that is like 1/10 of the diameter of the moon. There are already 10,000 galaxies in this little patch here, and if you zoom in, it's full of galaxies. And in this picture, there are only like 4 stars. The rest is all galaxies. And again, on these galaxies, and as I noted earlier, there are billions or trillions of galaxies in the universe to explore and to study the evolution of galaxies. That's one of the main subjects of radio astronomy in particular. And if you look at different wavelengths, here is the big Andromeda galaxy, for instance, viewed at different wavelengths. You can see the hot gas radiating in the X-rays to massive stars in the ultraviolet, the visible, that you can actually see this galaxy with your blank eyes. Then the infrared, showing cold dust and molecules and hot electrons at long wavelengths. And it looks different in every wavelength. Our favorite one is this wavelength range here, where that's the far infrared submillimeter to radio transition. That's where CCAT and project started out, and the FYST telescope is really tuned to, because we see dust, we see molecules, and hidden star formation and hidden galaxies. Even here I'm pointing at this because 2 in the audience actually contributed to this paper. If you look in the deepest Hubble Space Telescope images, there's nothing here. But if you look in the submillimeter with ALMA, for instance, you see a bright, that's indicated by these contours, bright galaxies. So many galaxies aren't visible even because they're so highly obscured by the dust that we saw earlier in our Milky Way plane, that we need submillimeter to look deep into galaxies. What do we actually see? Here is one central plot that I want to explain briefly, and that's the spectrum of a, let's say, typical galaxy. Here's the wavelength, from long wavelengths, the radio regime, all the way to the gamma rays that I mentioned earlier. And this is the energy distribution of the galaxy. If you take the entire galaxy, and the galaxy contains, in this case, also an active galactic nucleus. And what we see here is, first of all, two components. There's a continuous emission that goes up and down. Particularly here in the millimeter, submillimeter, we see the infrared emission of these dark clouds that obscured our view into the Milky Way. And that is reprocessed light from massive stars, very young stars, and that is absorbed by these dust clouds. Then you see on top of that lines, emission lines here of molecules like CO, but also others that give us indication on temperature, on pressure, on the abundance of the heavy elements, particularly carbon, oxygen, nitrogen, and so on. And these atoms and ions, therefore ionized, also have emission lines here, in particular in the submillimeter. They're very interesting indicators that we want to study in great detail. Then in the visual domain, we essentially see stars, stellar light, and then X-rays from hot gas, and that may vary depending on whether you have a AGN of a black hole accreting matter in the center of the galaxy or not. The submillimeter is particularly interesting because we have access to all these emission lines, and we have access to a lot of the luminosity that comes from star formation through this big infrared bump here. There's a problem with looking at that, our favorite spectral range, and that is the atmosphere. As Martha already mentioned, this is the atmospheric transmission over this wavelength range. And there's a transmission that's roughly 1 in the radio here, and it's in the visible range where eyes are sensitive. It's pretty transparent, but then in the hard X-rays, gamma rays, nothing gets through, and in the infrared, in the submillimeter also, it's absorbed. And here's a pretty picture I found indicating, again, over the spectral range, where the radiation gets absorbed in the upper atmosphere, particularly the hard radiation is important because we would get sunburned or cancer from that. Then the visual, where we can observe with telescopes from the ground, but also from space. There we have to go to space to detect these photons. Here in the infrared, in the submillimeter, we can build telescopes on airplanes like Sophia, and then the radio is transparent again. And this is here where we're mostly interested in. And to actually observe here, we have to go to a high and dry site. And as Martha indicated, because it's the water in the atmosphere, it's the water vapor in the atmosphere that absorbs mostly in this infrared submillimeter range. And was it 97 or so where they started exploring the ALMA site? This is where ALMA is done here, and the apex and so on, and found one site, Cerro Chajnantor, 600 meters higher up there. And this is a very important picture of what we call atmospheric windows that open up when you go to this high dry site. And this is a comparison of the atmospheric transmission. High is good, low is bad. You know, how much gets actually through. This is like 50% of the radiation gets through. And this is from 200 micron, 0.2 millimeter wavelength to about 1 millimeter wavelength. And you can see here it opens up, but we are really interested in this domain here. Here it gets pretty difficult. And this figure shows you a comparison of some of the best astronomical sites, where CCAT or FYST will have 10% of its time, 50% of its time, or 25 and 50% of its time transparency here. So that's pretty good, 40, 30, 40%. In fact, and then compare that to the ALMA site, which is this pinkish here, and Mauna Kea, which is also a very prominent astronomical site on Hawaii. So you can see that for about, we get 50% transparency, or for 50% of the time, we get a transmission larger 37%. Why is 37%? That's e to the minus 1. That's an opacity of 1. We get a better transparency than that for half of the time. And that's extraordinary You may say, okay, but ALMA gets a 2, but that's a factor 2. Factor 2 means a factor 4 in observing time. This is dramatically different from here to here. And we get even for 10 or 20% of the time very excellent observing conditions, particularly in these submillimeter windows. In between, water vapor absorbs the radiation. And then this is really our highlight summary, giving the decision to build up there under these extreme conditions and expenses. You can see this 37% corresponds to that point here. That means we want to observe with an opacity in the zenith better than 1, meaning that more than 37% of the radiation gets through in this domain here. And you can see this is the cumulative time that we have in these observatories. And we're observing not only now ALMA and Mauna Kea, but also the South Pole, which is considered one of the best sites because it's so dry, everything's frozen out. However, the South Pole is even worse than Chajnantor because it's too cold. And the water vapor has transitions in there that actually make it more obscure in these submillimeter windows. So our site is not only great compared to other astronomical sites, it is actually the best site to observe at these short submillimeter wavelengths on Earth. Not only accessible, it's very accessible as you will see, but there is no better site in the world, and that's why we chose to go there under these extreme conditions. And that makes it also in company, many of the great observatories are in the southern hemisphere, are being built, like the Vera Rubin telescope here in Chile, the ELT, a 40-meter optical telescope going to near infrared, the VLT, ALMA, and so on, Simon's Observatory, and then also some of them in South Africa. And CCAT is going to be one of those great, FYST is going to be one of these great telescopes that we'll have in the southern hemisphere accompanying this array of amazing observatories that we have. They will all complement each other in how they can view the universe with different wavelengths. To explore a lot of different phenomena I don't have time to get into, but my colleagues will this afternoon from magnetic fields, dust and molecules, hydrogen in different forms in the cosmic microwave background. It's not only these different phenomena that we see the time evolution of the universe through looking back in time, and of course, can't miss mentioning many Nobel Prizes went to radio astronomy for many of these discoveries, many to come, hopefully. And this is a diagram that you'll see probably again this afternoon. This is sort of the time evolution that we can follow with these observations from the very early Big Bang, where we're trying to find polarization signatures in the cosmic microwave background that get us back to like 10 to minus 40 seconds, or 10 to minus 35 seconds or so after the Big Bang, very, very early. Then the cosmic microwave background that has lots of interesting signatures on it, and Eve is going to talk about that. Then the dark ages of the universe. This is sort of a two-dimensional temporal evolution of the universe from the Big Bang to today's. And then there's this cosmic dawn. Renée is going to talk about that a bit. And galaxy evolution, Manuel, Aravena will talk about that. It happened a bit later. And then today's universe, the present-day universe, that we also are going to have a few talks by Amelia and Doug. So not only can we study different kind of phenomena, we can actually explore the evolution of the universe through them in a very unique way in the submillimeter domain. I hope I gave you a little bit of context for that. Thanks for your attention. Lots of open questions. Yeah, lots of open questions there are, certainly.
Thank you very much, Frank, for the very illuminating talk. So the next speaker is Steve Parshley. Steve is a very interesting man. He worked with me starting in 98 or something, or 2000, And Steve is magnificent engineer. He's the chief engineer from the Cornell site. And what he has done that's remarkably is he's built several instruments. He's building this, he built the telescope or supervised it. And this man wintered over at the South Pole with one of our instruments and ensured that we got spectra in that 200 micron window that was pointed out as so difficult. And he's quite a hero at doing that. So I'll get off the stage.
Thank you, Gordon. Okay, there I am. Great. So yeah, happy to be here today talking to you guys. I have the fun talk. I get to talk about the telescope. I like to tell people I have 2 children. My daughter is 6 years old, and FYST is 10 years old. So I'm going to, I sort of copied Martha's talk in the sense that I'm going to start by thanking people. She thanked a lot of people, but I want to specifically thank all our reviewers that we've had over the years. They were a tremendous help to the project, and I don't think we'd be here today without them. So Dean Chalmers, Ralph Booston, Richard Hills, Jeff Mangum, Jeff McMahon, Art Sims, Dave Woody. Dave Woody was especially helpful at the beginning of the project when we were in conceptual design phase. And Richard Hills, who sadly passed away in 2022, really took a shine to our project after some of the reviews, and he helped us quite a bit with the optics and with holography, and I'll get into some of the details of that later in the talk. Also have to thank all our amazing contractors, which you've already heard about a little bit. You know, the fact that we're doing this at 5,600 meters is really kind of unprecedented. We're the second highest construction site in the world after Tau. And I'm not going to read through all of these, but I have to highlight Vertex, of course, CPI, Vertex Antenna Technic. They are the prime contractor on the telescope, and these guys, Peter, Klaus, Carl, Jorg, Scott, Marcus, Marcel, Bernd, Olaf, Neil, Sven, Heiko, Ralph, Roxanne, Roland, and Conrad, and the rest of the team, they were all just tremendous people to work with, and I really, really appreciate them. Finally, just a big thanks to everybody here, all our friends and the greater CCAT community. 2 people that I left off this list that I'm just going to say, Chuck Henderson and George Gull. They were engineers at Cornell when I first started, and they were very kind to me and helped mentor me, and I owe them a huge bit of thanks. And finally, thanks for all of the astronomers who we're building this for, and all the future astronomers, and I can't wait to see what they're going to do now that we've built this sucker. So to give you kind of some of our lingo, when we talk about the telescope, no pointer. So the central part here that I've highlighted in purple, that's what we call the elevation housing. That's what holds the mirrors. This U-shaped structure, we refer to that as the yoke. And so the yoke has 2 arms on it. On the left side is yoke arm A, where the instruments are located. On the right is yoke arm B, that's where the elevation drive is. Those are on top of a yoke traverse, which is actually separated into an A, middle, and B section for transport. Stick. Sweet. All right. And these are all disassembled for transport and reassembly here in Chile. This whole thing sits on top of the support cone to rotate in azimuth, and then we connect to site services through the main power distribution container here in the corner. So just to give you some key technical features of FYST, what makes it special, you know, we have a very large field of view that lets us look at lots of the sky at once. We have a large focal plane that lets us get lots of detectors lit up at once. We have a shutter to keep the snow out, because it snows up there quite a bit. And we don't want snow getting on our mirrors, or at least unnecessarily. We have advanced metrology. We have our mirror support structures are made out of carbon fiber. That provides a really great stiffness to weight ratio, which is what we need to basically build a telescope with these specifications. Overall, it's a pretty big beast. You'll get to see it tomorrow, but it's about 15 meters tall, 23 meters long, and almost 6 meters wide. That's the yoke structure. The elevation structure is even wider to hold the mirrors because they're 6 meters in diameter. And the mirrors, each one weighs about 2 tons. That's inside the elevation housing, which rotates. We have about 50 tons rotating on the elevation axis. That in turn is supported by the yoke, which rotates in azimuth, and that's about 200 tons. And we got about 220 tons total sitting on the foundation. So it's a beast. And speaking of the foundation, Martha mentioned this a little bit. This is just another picture of the foundation and how we did it. We decided to do a precast, combination of precast and in situ concrete. So on the left is the CAD model. The brown or the gray is the precast elements, and then the green is all the in situ concrete that we did at site to knit it all together and make it one solid monolithic foundation for the telescope to react against. And so all in, this is about 500 tons plus the leveling concrete layer. So there's another picture of the site where we dug a hole to put this thing in. Okay, then I want to talk about the optics a little bit. So we started in 2016 with Mike Niemack's applied optics paper. Here it is, the design for a large aperture telescope to map the CMB 10 times faster. And this is a cross-Dragone design. You can see here he had a tertiary flat fold mirror to direct the radiation into an instrument. And I really consider this the genesis of FYST. This is really what got us started. In 2017, we advanced the optical design. We still a 6 meter cross-Dragone, but the optics got a little bit faster. And this is where Richard really came in and helped us out a ton. He implemented this coma correction to the optics and also discovered this really elegant, I think, I call it the 3, 4, 5, 6 design. This is a 3, 4, 5 right triangle. So he discovered that, and then this distance here from the optical axis to the focus is 6. So you pick your scale size and multiply by 3, 4, 5, 6, and there you've got your optical design. Bam. It's really nice. The coma correction that I mentioned, so this is also what Richard implemented or helped us with, and this is the original diffraction limited field of view here for the cross-Dragone design, and here's the improvement that we have with the coma correction optics. And you can see the colors just represent different wavelengths where we're diffraction limited. And in the submillimeter, it's the greens and the blues that you want to look at for the submillimeter. So you can see we have a substantial improvement in our field of view, in our usable field of view at the submillimeter with these new optics. Okay, so the coma correction is really we're just having a slight deviation to the mirror surfaces from a pure conic. So the mirrors still have symmetry. They have mirror symmetry. Left and right look the same in the mirror. So a panel on M1 in the second row, first column looks the same in the mirror as a panel on M1 in the second row in the ninth column. But what this means is that the panels are unique. So we can't move a panel from somewhere else and have it work in a different position. So it really comes down to tolerancing and positioning. And here's just some plots of showing you the deviation that we applied to these surfaces from their pure geometrical surface. And it's actually, you can't read the plot, but basically the color scale here is less than a millimeter. We're talking about less than a millimeter deviation over the pure geometric surface. Speaking of the panels, they are machined out of aluminum. Here's a front picture and a back picture. I think the back picture is more interesting because that's where all the light weighting takes place. They're basically 90% light weighted, machined out of solid aluminum. Each one covers about a half meter of area. They're about 70 centimeters on a side. We have 77 of them for M1 and 69 for M2. And they're positioned with 438 locators, so that Vertex did that. They aligned them in Germany, positioned them where they needed to be, and then we do the vertical alignment with 730 adjusters. And to do that, we have a couple. That's a project deliverable, and so we have some options to do that. The first way is to do tower holography in a new way. Holography has been the way that you align a submillimeter telescope for all previous telescopes. The problem with doing that for FYST is we have two large mirrors, and so you need to break that, detangle the two unknown surfaces somehow. And so again, Richard helped us tremendously in developing this concept, and we've actually demonstrated it in a lab on a scale test, and we're ready for deployment. So we're excited to use that. That'll be a great paper. The other way that we're looking at doing this is we have a custom laser metrology system. So you can, the off-the-shelf stuff just would not work for FYST. It's not accurate enough. So we went to a company and developed a custom-made system for the telescope that'll basically ride along with the mirrors. The way this works is you basically triangulate a probe. So you have a cat's eye probe that you move across the surface of the mirror, and then up in the corners here. So this was a test setup that Ronan and I put together in Germany, and we reproduced the geometry of the telescope in this facility, and this is M1 that we were testing on. And so we've got 6 of these, they call them satellites, 6 of these satellites arranged around the mirror that look down on the probe, because you end up with this huge mass hanging off the end. So we went back to the initial design, refined it in September, and gave this to Vertex, and this sort of kicked off the conceptual design studies. And then Vertex ran with this. So this was their conceptual design coming from their preliminary design review. You can see the mirrors are contained inside the elevation housing. We've got kind of a dome shape to the top, and we've got this instrument and people mover over there on the side. And then here's their final design from conceptual design study. Some refinements there. Got rid of the dome. The shutter is now a sliding shutter as opposed to a flap that opens. And then we started with detailed design. So here we're Vertex's preliminary design review from March of 2018. You can see the large lift that was supposed to move people and instruments. We downgraded that to just a people mover on the side. That's the blue box. And then we're going to lift instruments with a crane from the instrument space. You can see the form is starting to take shape here. And then here we are at critical design review. This is October 2018. The lift hasn't changed. The aperture has. We went from a circular aperture on the elevation housing to sort of a maximum aperture there. You can't see it, but there's a lot more detail going into the design and into the structure. And here's one thing that changed. So the critical design, we're still connecting to site through the support cone. And then at final design review, we divorced that. We said, okay, we'll have our connection in this, what's now called the MPD, and we'll trench between those two. And you can see here all the details are really taking shape in the final design. And that was November 2019. So what makes FYST next generation? Basically, all these things. Scale, it's one of the largest submillimeter telescopes for survey, submillimeter survey telescopes ever built. Because of the optics, we can put instruments on, and you'll hear more about this in the day, about, the types of instruments we can put on. They're multi-band, the multi-science case suite that people have worked on. It's really quite impressive, I think. Of course, we have a generous payload capacity. We have the novel mount design where we can observe past zenith and look on the other side. And we can also stow the telescope at minus 90 to help protect the mirrors. And of course, our infrastructure is built to match all of these capabilities. So I think this is really going to open a new era for wide field regular cadence submillimeter astronomy. And I hope it bridges the gap between these targeted high resolution observations and all sky surveys, and will provide foundational data for years to come. I'm really amazingly proud and pleased with the team, and here's some pictures of mirror installation. And yeah, and there's the team after, on the left, after M1 got installed, and here on the right, after M2 got installed. And that's it. Now we're ready to see what this sucker can do. Thank you.
Thank you, Steve, for the excellent talk. Next speaker is Mike Niemack, Professor Mike Niemack. He's from Cornell. You came in 2012, if I remember correctly. And at this point, we had the 25-meter version, and we had some disappointment with funding from the NSF. And Fred pulled us through, and Mike brought in this new design, which really, the cross-Dragoni design, which really was a tremendous shot in the arm, and I thank you very much, personally.
My pleasure. Thank you, Gordon. Buenos dias. Thank you all for coming today. It's really, this is working, yeah. Pleasure to be here and to meet so many new friends and colleagues and catch up with so many old ones. So anyway, it's a very exciting time, as you can tell, for the project, and now I'm happy to have the chance to talk to you a little bit about the PrimeCam instrument that we've been building at Cornell, this next generation astronomical camera for FYST. And you can see a recent photo of FYST up on the left with both mirrors installed, as Steve was describing, and a recent photo of the PrimeCam instrument that I'll be telling you about here, with labeled by the different wavelengths of light that we're currently building instrument modules for, as well as a couple more that we're planning and applying for funding to complete the instrument and then continue upgrading it over time. So as Frank mentioned, and you'll hear about more this afternoon, there's really a broad range of science goals that we're pursuing with PrimeCam. And combining FYST and PrimeCam will be able to make the most sensitive submillimeter wavelength surveys yet by an order of magnitude or orders of magnitude, depending on what aspects of them you're looking at and how we quantify it. Right? And part of this, though, which I'll talk about now, is we'll be deploying the largest scale deployment of these novel KID or kinetic inductance detectors yet in PrimeCam just later this year, and then upgrading it by almost an order of magnitude over time. So just to give a quick orientation, right, here's another timeline of our universe, starting with the Big Bang on the left, that Eve, who you'll hear from later, Vavagiakis, put together. Cosmic microwave backgrounds release for stars and reionization. We'll be doing a CMB survey, a reionization survey, dusty galaxy survey, and we get to more and more recent history, where there's a small timeline on the bottom here, galaxy cluster survey, and then galactic surveys, all measured with PrimeCam, as you can see, these hexagons in the upper right. So I won't talk about that. Again, you'll hear more about it later, and get to see FYST soon. And here's just a recent photo, a little bit older photo, of some of the PrimeCam team members looking through various holes in the instrument. So you can see the scale here. Anyway, that I'll focus on now. So I just also want to recognize and thank the members of the PrimeCam team. These are really, many more people have been involved in conceptualizing this and planning the surveys and things, but these are the people that, hopefully it's all up to date, that are really focused on the hardware and instrumentation development. Just to call out a few that are leaders within the PrimeCam team and here today. Abby Kreitz at Cornell, who, anyway, you can look for each of them. and ask any of us questions about this throughout the next couple of days. Myself, of course, Gordon Stacy, who's been introducing us, and our project director, Vavagiakis from Duke University, as well as Scott Chapman from Dalhousie. Also want to recognize our funding sources. We've been supported by the National Science Foundation, the Canadian Foundation, Canada Foundation for Innovation, as well as partner university contributions throughout Canada. Fred Young Charitable Trust, of course, Cornell, and a little bit even from NASA, although they don't focus as much on the ground-based telescope, unfortunately. So you've heard about this a little already. I just want to show you a different plot about why we're going so high, right? We have this great telescope and camera. We want to put it at a great site. And here's a photo of the Chajnantor Plateau and the ALMA Observatory in the foreground at 5,000 meters. And we're going all the way up to 5,600. So they're both great sites, but as has been described earlier by Frank in particular, if we look at the mapping speed as a function of wavelength on the x-axis here, and so this is how long we need to integrate with one of these telescopes in the top, and this is the top 75% of the time. So 75% of the observing conditions, just by going up this extra 600 meters, we get a factor of 4 improvement in our mapping speed and can dramatically improve the measurements that we're making compared to being down at the ALMA Plateau. And to highlight the complementarity between CCAT and FYST and PrimeCam and our colleagues on Simon's Observatory, which is off to the left on the side of the Cerro mountain at 5,200 meters. Simon's Observatory is really focused on these longer wavelengths, centimeter to millimeter, basically. And with CCAT and FYST, we're going millimeter to submillimeter, where we see these enormous gains from going to the higher elevation site. So here's a cross-section. Steve's already introduced this to you well. And we'll be putting PrimeCam in this instrument space 1 here, the larger instrument space. And you'll hear about Chai that's being built in Germany that's going into this instrument space 2 down below next. Here's another photo of us after we closed up the PrimeCam instrument at Cornell recently that's going into instrument space 1 there. And again, this will have many times the mapping speed of previous submillimeter instruments. And I just have a little animation here to show what Steve was describing. Light coming in from the sky, bounces off the primary mirror, off the secondary mirror, and then is focused right in front of the PrimeCam instrument. And I'll show another one in just a moment about what that looks like inside the instrument. So a brief overview of PrimeCam is we're, of course, aiming to pursue exciting and unique science, astronomical, cosmological science with this instrument, and to use a large fraction of the awesome FYST field of view. And that's why we're building this large instrument, almost 2 meters in diameter, where all of these hexagons can collect light as we upgrade the instrument over time. This is designed with these 7 hexagons, as I was just describing, that can each host a different instrument module, and 3 of these detector arrays per module. The initial instrument module capabilities that we're pursuing are 4 of these broadband modules at each of the wavelengths indicated here, and then 1 spectroscopic module to go after, in particular, this reionization science, spanning from initially around 0.7 millimeters to 1.4 millimeters. And then thinking about these on-chip spectrometers in the future that we want to put into some of the additional instrument module slots in the coming year. So these first 5 are the ones that are funded and under really active development right now, as I've listed on the lower left here. So, right, what are some of the key technologies for this instrument? You can see in the upper right, here's a diagram that Eve also put together, highlighting some of the cryogenics and optics systems that go inside this large instrument. And we need to cool these detectors, these kinetic inductance detectors, to minus 273 Celsius. So almost absolute zero, 0.1 Kelvin, a tenth of a degree above absolute zero, to get them to operate properly and to be as sensitive as we need them to be to take advantage of this awesome site in the Atacama. So we have refrigerators in the instrument here. At the very top, there's a dilution refrigerator that cools these things down to 0.1 Kelvin, and then intermediate temperature stages of 4 Kelvin, 1 Kelvin, 4 Kelvin, 40 Kelvin, and 80 Kelvin that we need to cool different parts of the system to make it all work. Within each of these instrument modules, so here's a diagram of one instrument module and then a photo of one just before it was installed, and I'll show a little time lapse of it being installed in our test bed in our lab at Cornell in just a moment. Within each of these, we have lenses, just like you might have if you have an older camera, and I guess our phones have small lenses on them as well. But here we actually have 3 large lenses, about 40 centimeter diameter silicon lenses that are really pushing the boundaries of optical, submillimeter optics technologies to make this work, as well as filters to select the wavelengths of light, and then these kinetic inductance detector arrays that are in the back here, I'll show some photos of in a moment, we're really pushing the boundaries of that technology as well. And they're taking up a good amount of our time. But it's coming together really nicely, and we're on track for first light later this year. So I mentioned, looking at the light traversing through one of these instrument modules. And so here, if we look at a point, light from one point on the sky that was focused by the telescope up front here, then it goes through these 3 lenses and gets refocused down onto the detector arrays. Now, if we look at another point on the sky in blue now, it's coming in through a different part of the entrance, it's focused to another position on a different detector. And so in the first 2 modules that we're building, including this one shown here, we have 10,000 of these detectors in each of the modules. And so each one is actually looking at a slightly different position on the sky. And these optics are focusing the light onto them. So that enables us to map large regions of the sky quickly with this instrument. So here's just a time lapse. It's a few years old now of our first attempt to install one of these instrument modules into our test bed. So this is a ModCam instrument that is just our test bed for these at Cornell. And these are grad students, postdocs, and faculty members working together on this. And it didn't quite go in right the first time, so we pull it back out, make some adjustments, try again. Still not quite there the second time, but third time's a charm. And this is what a lot of our work is like on a daily basis as we're getting these instruments working and these unique, never before built kinds of cameras working for FYST. And I mentioned kids taking up a lot of time. Here's our youngest. She's grown up a lot over the last few years, just like our kid technologies, from a little hippo to driving and teaching me how to use my computer. But anyway, these kids are a relatively new technology. They're maturing quickly, like my daughter, we're helping to rapidly advance them both for FYST and for the field as a whole. Because they're really an exciting new enabling technology. And we're experimenting with different materials. We have a titanium nitride kit array. We're making some aluminum kit arrays, and those are the 2 primary materials that we're using for these detectors. I'll just highlight roughly how they work here. So each of these kids is a resonant structure, an electrically resonant structure that if you've taken any electricity and magnetism classes, it's an inductor and a capacitor. They're cooled to very low temperatures, as I mentioned, and we excite them with electronics that will drive them and measure them at a particular frequency And then as the light increases from the telescope, the frequency will shift and the amplitude of this resonance will decrease as well. And so we have, one of these modules, 10,000 of these that we're tracking with digital high-speed electronics that we've been developing in close collaboration with Scott's group in Canada and others. And here's just a couple photos of individual kids. One kit array with over 3,000 kids on it. And then our first set of 3 arrays that have 10,000 kids in them. One of the instrument modules installed in PrimeCam, and some of the high-speed digital electronics that were packaged at Arizona State University with the firmware developed in Canada. So these are some of the largest and most advanced kit arrays ever built, and when we deploy 20,000 of them later this year, it will be more of this type of detectors than has ever been deployed on a telescope before. And that's just the beginning. That's just 2 of the 7 modules that we'll be deploying this year. The other 3 aren't ready yet, but over the next couple of years, we'll be upgrading that to over 100,000 kids. So over an order of magnitude growth in these detectors compared to all previous deployments except one that's under 20,000, not quite an order of magnitude at all. But that's really the scale of improvement that we're pushing towards, order of magnitude scale improvements in capabilities for submillimeter astrophysics. I'll wrap up quickly here, but just to highlight some of the optical testing that we have to do before we deploy any of these modules, and fully integrated module testing, where here this was our first attempt to measure the positions of many of the detectors, and we've made improvements since then, just in the laboratory with a source, the light coming in through this white window here. And then here is actually measuring the wavelengths of light that these detectors are sensitive to, and we say it's a 1.1 millimeter instrument, although it's actually, with the broadband ones, sensitive roughly to between 1 millimeter and 1.2 or even 1.3. Anyway, as an example. So there's really just been a tremendous amount of work on this instrument, especially over the last year. It was delivered a couple of years late from the shell manufacturer, and was delivered in February 2025, just these empty shells with no instrumentation inside. It held vacuum, that was great, the first test we did, but there's been a series of many cool downs and upgrades over the last year, and it was awesome to see when a postdoc at Cornell put this together. It's all come together, and we're making optical measurements through PrimeCam with the first instrument module just a year later. And just to give you one last sense of the work that we're doing in the lab and that we'll be doing on the telescope later this year, right? These are big components that we have to assemble, get together, make precise connections between all of them, get the cryogenics working, the optics working, all the electronics working. And again, we'll be deploying 20,000 kids later this year, most kids on the sky yet, aiming for 100,000 by 2028 with these additional instrument modules. It'll be the most sensitive submillimeter instrument ever built, and there's potential to upgrade even this instrument as we advance the low temperature detector technologies towards megapixel scale kit arrays in the future that could really open up new windows in submillimeter and millimeter astronomy and astrophysics. So this is it. PrimeCam will ship from Cornell to Chile in about a month. We're taking it all apart now. We purchased 2 40-foot shipping containers and have started loading some of the equipment into them. And yeah, here you can see the first time we put an instrument module into PrimeCam, that time it went in the first time. We learned some things from our earlier attempts, and it's really been awesome to work with this team, both at Cornell and our collaborators all over internationally and across the US, on bringing this together and pursuing this science coming up soon. So thank you.
Thank you, Mike, for the great talk and good luck. His team is doing an incredible amount of work right now. So the next speaker is Dominik Riechers. Known Dominik for a while as well. Dominik was a professor at Cornell for 5 years or so. 9? Oh my goodness. Time warp. And my good friend and colleague, Jürgen Stutz, he was at Cologne at that time, and he, same age as me, but was forced to retire. I wasn't. And Dominik, fortunately, took his position and took his enthusiasm for the project. So looking forward to your speech.
Yeah, thank you. Yes, I hope now that it's clear what the vision is that we have in Cologne for contributing to FYST and the science that we're going to do. My colleagues at Cornell can forgive me that I left, because I think it makes the project as a whole bigger, the way that we can do things now at the position where I am. So I'm going to present the second instrument besides PrimeCam that will go on FYST, which is the Chi Spectrometer. And before I get started, here's the time to talk to the audience. So may I ask who in the audience is not an astrophysicist? Please raise your hand. Probably about half the audience. Yeah, because of course I could now go on and tell you that what we're building is the best instrument of its kind, that goes to the best telescope of its kind, and throw a few numbers at you. And I'm going to do that towards the end. But really most of this talk is targeted towards you who are not astrophysicists. So the experts will hopefully forgive me for the introduction, but this is what I'm trying to do here. All right, so the instrument we're trying to build is called Chi, and this will go, as Mike has already indicated, to the second instrument space in the lower part of FYST. And with this instrument, we will do spectroscopy. All right, and before I start in the details, also for me, thanks first to our funding sources, which of course is to a great cut the German Science Foundation, who is also represented here through a range of programs, as you can see, without which this would not have been possible, because really most of our funding comes from the German Science Foundation. But then, of course, we also have base funding from our university across different kinds of funds that makes this possible, especially to keep staff engaged long term to make this possible. And then also we have collaborators in Bonn at the Max Planck Institute for Radio Astronomy that help with parts of the technology, particularly what we call the readout system. And then, of course, also big thanks to the country of Chile and, of course, the sky over Chile, which is what we actually want to observe, and the Chilean astronomers who are involved in all of this, in particular also the science. And you're going to learn more about this in the afternoon, where you will recognize that a lot of the speakers actually are from the Chilean community, because people here are also excited about what we're doing. It's not only us. All right. But with this, I want to get started. So what we want to do is we want to detect, of course, astronomical sources and learn something about them. And since I'm going to describe an instrument, the question is, how are we going to do this, and what are really the fundamental principles and the components that are important to do this? And if you think about astronomical detection, the way that you can imagine is that you have some object on the sky that you can resolve into pixels, right? And then the light that comes from the sky, you have to focus in some way onto some sensors that can actually detect the radiation that comes from the astronomical sources. And then we need some sort of a readout system, some readout electronics, to actually be able to learn the information from the detectors and bring them onto our computers and translate them into the information that we want to know. So these are really the fundamental components that we're dealing with. And all of this goes also back to the fact that, of course, when we detect light from the sky, what we're detecting actually is something that carries energy. And of course, we all know this, right? For example, being here in Chile, we of course all know that sunlight warms our skin, and if you're not careful, we get sunburned. This is of course because we get an energy transfer from the radiation that comes from the sun towards our skin. And then of course, we also know if we can turn the sunlight into actual electricity by using some elements like this. So therefore, we know that the light that actually comes from the sky carries energy. And we can actually express this energy relatively simply, because the energy that light carries is just given by the frequency of the light and a natural constant that we call Planck's constant, that is this little h in front here. And therefore, the only difference between different kinds of light that we receive is really only the frequency of the light. And of course, we can imagine this first by color. So essentially, higher frequency light is bluer and lower frequency light is redder. Or also we can imagine this acoustically. For example, if you go to a concert, then if you hear the sound from a guitar, it will be at higher frequency than what you receive from a bass, right? So this really is how we can tell the difference both with our eyes and also acoustically. And this is, of course, what we want to do also from space. So when we receive signal from space at different frequencies, then these frequencies we want to be able to tell apart, in particular in the submillimeter with the telescope that we're building, as we've learned already. And also, we receive different kinds of light from different sources because of their nature, but also the characteristics of the light will change based on the distance, but that's something we'll learn about more in the afternoon. I have to resist telling you more about this because this is really exciting, but this is what we want to look at. Okay, but the base principle also, of course, we all know very well because you all have your mobile phones here. You probably took many pictures being here in Chile, and what, of course, you detect there is not necessarily the structure itself that you see, but what you really see is the sunlight that's being reflected off the trees or the mountains that you're seeing, not the emission from those objects themselves. And of course, we can simply see this by switching the sun off or going to nighttime. You cannot see the mountain anymore because it's not radiating itself. So what we're seeing is the sunlight being reflected off these objects into your mobile phone through a lens and onto a detector within your mobile phone that actually collects the radiation. And then when the light hits the sensor, the state of the sensor will change. And then if you use some sort of electronic circuit to read out the sensor, then this will tell us that yes, whether or not there is radiation and also how much of it was detected there. And then we can use this to reconstruct the picture, right? So this is a general idea that's behind it that we know from digital photography. And the principle behind this is really also the same with what we want to do here. However, there's one major difference, which is that the sunlight that you receive is light that's very bright in the visible, and that's very highly energetic radiation by comparison, whereas the light that we're trying to detect from space with our instrument is light that is in the CVC in the submillimeter that's coming from, in particular, cold gas and dust. And this radiation carries about 1,000 times or a few thousand times less energy than the light that we can collect in the visible with our mobile phones. And this means that the technology that we need to collect this light is, of course, different and much more demanding. In particular, to get to this low energy, it's very important that we're able to cool the instrument. So the way that, therefore, we can imagine what such an instrument looks like is here. So we have some sort of an enclosure, and then we have light coming onto the top, and then there's some sort of detector inside the instrument that's going to detect the light. But then the whole detectors themselves need to be cooled to very low temperatures, and as Mike has indicated, this is very close to the absolute zero, so the lowest temperature that we can produce, very close to the absolute 0 point. So the detectors will be at that temperature because then they can detect even the small energy change that's produced by this low energy light that's coming in the submillimeter. And this is the principle behind it, and cooling therefore is so important. And how important this is something that you can see from the whole system, because I told you there's an additional component, which is the readout electronics, which means you send a current in to ask, did you detect something or not, and how much of it. And even just sending the simple electricity through can mean that if you're not very careful, that you're injecting more energy than it's produced by what you detect from the sky, and therefore you're blinding your detector. So it's also very important that you develop some components that can do this readout in a way without destroying the signal. So these are really the factors that are important in building such an instrument, but there's one more important point, and this is the point of what we call spectroscopy. And this is also something that we're familiar with because, for example, if you listen to the sound that a violin produces, right, it doesn't only produce a single sound, but it produces a range of sounds. And in particular, there's these overtones that you get from a violin. So if you plot the spectrum of your violin as a function of frequency, which is just indicating the different notes, then you see, right, these peaks at these different notes, and here's another indication of that, what this looks like within the violin. And indeed, if you're able to tell apart this spectrum of the violin, then what you're able to tell is not only what kind of violin that you have, but also the builder and other things, right? So from all this fine detail that you can measure, you can figure out a lot about the violin. And without this information, you might be able to tell, okay, there's some sound, there's probably a violin somewhere there, but you don't have any detail in the information. And this is the same problem that, of course, we're dealing with in space. So we get signals at a range of frequencies, and we want to be able to tell these frequencies apart. And this is really what we're doing with high-resolution spectroscopy. We try to separate apart these fine signals, these fine frequencies from each other to learn about the characteristics and the nature of the astronomical sources that we're trying to detect. And this sometimes also what we call fingerprinting of astronomical projects, because we're going to see their composition, their excitation, and other things just from looking at the frequency spectrum. And this is really what makes Chai special. And of course, it's also something you're familiar with. For example, right, if you look at the sun, you might have seen that it has, of course, a color spectrum, but then also by resolving this, one can detect different lines in the spectrum of the sun, which actually tells us something about the composition of the atmosphere of the sun, and is an extension, again, of that principle. All right, but now let's come to what we're actually doing. So again, Chai lives there in our instrument space too, as we can see, and here's again just something for scale that shows you how big it all is. And then what you can see here is the instrument in the lab, or at least one part of it in the lab. So what you see here is this cooled enclosure, right? That's kind of what we've seen in the previous picture. And then there's some coolants on top. And then in the background, you can see these cooling compressors that are keeping everything at very low temperatures. And then at the other end, we have this supercomputer rack, which is really what is this readout system that we talked about that reads out the sensors, that was developed by our colleagues at the Max Planck Institute in Bonn. And then, of course, we also need some software to read out the entire thing and to monitor its state in the telescope. All right, so since the door is closed, let me just show you a few graphics of what's going on inside. So again, what you can see on top is the cold heads and then some electronics in the middle. And then towards the bottom, as you can see here at the zoom in, is the detectors. And the golden part there is some just focusing optics, some lenses in front of the individual detectors. And then you can see at the upper part is essentially where the signal is being read out. And then what you see as individual detectors is something that looks like this when you zoom in. So for scale here, right, this line that you see at the bottom is between like 100 and 200 micrometers in size. And then this is all of the electronics that we put on top that leads to the signal detection. And this is really a system that currently can only be built at the University of Cologne, and this is the heart of what makes everything work. So we are the only group that has this experience at the moment in the world to build these systems. And we built 128 of these detectors. These are so-called superconductor isolator superconductors detectors that indicates how they work in detail. Right, we need superconductivity to make this work. And then these chips down-convert the signal to lower frequencies that come in to be able to actually read it out with the electronics that we have. So this is what the system looks like, and then with this we get a footprint on the sky that's shown here, overlaid on the Horsehead Nebula, which you might be familiar with, and the individual circles here show you the individual detectors, and the two colors show you the two frequency ranges that we target with these detectors. Then here's just essentially a few numbers of what the characteristics are. You have to believe me that this is the far best that has been done yet for such an array. And in particular, what we're going to target with these detectors is the CO photo-3 and 7 to 6 lines. Those are two rotational transitions from the CO molecule, and then two fine structure transitions from the carbon atom. And then what we get as information shown here is just an example from a star-forming region, right? We get, of course, images, but at every frequency, so we get this frequency spectrum and the change of what the source looks like at all of these fine different frequencies. And indeed, we have 128 spatial sensors on the sky, but with the frequency tone or the different tones that we can produce, about 80,000 of them, we get more than 5 million pieces of information every fraction of a second from the sky, from these astronomical sources. And this is really unparalleled to be able to read it out like this, and makes us an order of magnitude or more faster than any such system that has existed so far due to its scale. All right, so this is it, and with this I'm also happy to take some questions, and let's see if we actually have the PowerPoint and can make this run in the background. No, we can't. Okay, would have been a nice movie, but otherwise I'm happy to take questions without it. Thank you.
Thank you, Dominik. Leo Bronfman is our next speaker. He's a professor at the University of Chile, expert in star formation for many years, and the Chilean member of our board. And so I'm looking forward to your speech, which is about the history of astronomy.
Good morning. I have been requested to give a talk about astronomy in Chile. Of course, it will be quite brief because of the time and many things that I will not mention. So, everything starts with a Gillis expedition in 1849. At that time, Lieutenant James Melville Gillis from the U.S. Naval Observatory came to Chile in October 25, 1949. The purpose of his mission was to measure the solar parallax, the distance from the Earth to Sun. Yeah, okay, thank you. Observing the opposition of Mars and Venus at its third stationary point. He established his observatory at Cerro Santa Lucia in Santiago. This was the person, and this was the Santa Lucia hill from the east. The refractor he used in his observations. The president of the University of Chile at that time got interested in the project of Lieutenant Gillis in Chile. So did Ignacio Domenico, the close collaborator of Bello and the second president of the University of Chile. 3 Chileans, a professor of mathematics, and 2 of his best students were appointed by the government to train and help carry out the observations. So, in 1852, the National Astronomical Observatory in Chile was founded by decree of the President of the Republic, Don Manuel Montt, who purchased equipment to Lieutenant Gillis' expedition. So this was the first place of the observatory after Santa Lucia at the Quinta Normal Park in 1860. He stayed there until 1913. I'm going to skip a few directors. I'm going to Federico Ristenpart, who was appointed as the first director of the OAN. And he was important because he moved the observatory to Lo Espejo site, about who they stayed from 1910 to 1960. At that time, there were more instruments at the observatory, like the astrograph telescope Gautier, which carried out the carte du ciel. Then we jumped to 1950 with Professor Federico Rutland, who was appointed as director of the National Observatory and was in charge until 1963. He, most importantly, moved the observatory to Cerro Calán, where it is sited now. It was the last displacement of the observatory. But he was not only important for that, but by the fact that in the late 50s, Professor Rutland visited the University of Chicago, Yerkes Observatory, and talked to Dr. Gerard Kuiper, its director. Because Chicago and Texas were planning to build an observatory in the southern hemisphere. So Dr. Kuiper visited Chile later that year. And then came in 1959 Dr. Jürgen Stock from the University of Texas for a site testing campaign, who was carried out with help of the University of Chile personnel. So the project, Chicago, Texas, Universidad de Chile, was transferred to ORA as CTIO, Cerro Tololo Inter-American Observatory, which is right there in 1967. Not much later, we had Cerro La Silla Observatory from ISO, and the Carnegie Southern Observatory at Cerro Las Campanas. And then came from ISO the Paranal Observatory and the VLT, the Gemini South from ORA at Cerro Pachón, the 6.5 meter Baharian clay Magellan telescopes at Cerro Las Campanas from Carnegie, and at the present, we have the 8.4 meter telescope at Vera Rubin Observatory and Cerro Pachón, only one It was delegated on 2025. And the future is ISO 39 ELT, 39 meter ELT at Cerro Armazones, which is still in construction, of course, and the giant Magellan telescope at Las Campanas, which is 7 times 8.4 meter mirrors on the 25.4 meter wide light collecting surface. Now let's go to radio astronomy, which is called what convokes us today. Well, early radio astronomy in Chile was the Maipú Observatory, close to the west of Santiago, which worked from 1955 to year 2000. It was a very early design, 528 dipoles in 10,000 square meters, but it was the first in Latin America. We completed a sky map at 45 megahertz, which is the lowest frequency available still. Northern Observatory, Northern Hemisphere was observed from Japan. Then the Columbia University, Universidad de Chile 1.2 meter wave telescope, there was a collaboration. It's at 8-minute resolution at 115 gigahertz in Cerro Tololo. And it carried on the first complete CO survey of the galaxy with the Northern Columbia telescope for the Northern Hemisphere. Then it came the CEST, which is the Swedish ISO submillimeter wave telescope at La Silla Observatory in 1988. It was a 15-meter diameter antenna working between the 100 and 345 gigahertz frequency range with a resolution of 45 arc seconds at 115 gigahertz. By then, the ALMA site at Chajnantor was being explored. This was a picture of Chajnantor Pampalabola in 1996 with sky measuring instruments, already test instruments deployed. The first instrument at the ALMA site was the Caltech Cosmic Background Imager, the CBI, in 1999. Apart from the scientific endeavors, it was a test of the astronomical operations at the site. And also the first generation of Chilean radio engineers was trained at CBI. Then came the Atacama submillimeter telescope experiment, the ASTE, from Japan National Astronomical Observatory. The Nanten telescope, 4 meters at Pampalabola. And the Atacama Pathfinder experiment in the middle of the present ALMA site in Chajnantor, told me the telescope, which has been working since 2005, and very strong work, lots of data has been taken with this telescope, and many instruments have working there. And then the ALMA telescope, which science operations started in 2011. It was the largest submillimeter wave telescope in the world. We all know what it's about, 66 antennas, 54 12 meters and 12 7 meters, working up to 950 gigahertz. It's a North American, Europe, East Asia in collaboration with Chile. As Martha showed, a concession was established both for ALMA and another concession that was given to CONICET, presently ANIT, which has two reasons. The first one is to further protect the ALMA concession from mining another subjects that can damage the ALMA telescope. And the second reason was to protect the hills surrounding the ALMA plateau, where the CCAT project is developing now. Well, presently also the SIMOS Observatory is working at the Cerro Toco site. And finally, the TAO, Tokyo Astronomical Observatory Infrared Telescope, which is at Cerro Chajnantor at 5,640 meters of altitude. I will not talk at all about this, Fred Young's submillimeter telescope, because everyone has talked about this, and I'm talking about the rest of it. Okay, what has happened with Chilean astronomy? Now there are 11 PhD programs in astronomy and astrophysics at different universities. In year 2000, the Sociedad Chilena de Astronomía was created, and what is most impressive is this, in 2005, we had 59 researchers and 40 students. In 2023, 287 researchers and 784 students. So almost, well, it's a big growth of astronomy in Chile. Reason being of the observing time, that 10% of observation time at international observatories in Chile is reserved for astronomers working in Chilean institutions. And there's also some funding from ANID, which has scholarships for graduate programs and development. And also there are some international funds like the ALMA Fund, the Gemini Fund, ISO Fund, and recently the Vera Rubin Fund too. And finally, I will talk about some development of astronomical instrumentation in Chile in the last 18 years, with the support of the Center of Excellence in Astrophysics and Associated Technologies. The Catholic University has a drone-based calibration of polarization angle for Simon's Observatory program. The University of Concepción is moving to Cerro Toco the Leighton Chajnantor telescope, which is the ex-Caltech Submillimeter Observatory, with the help of the University of Caltech and Shanghai Normal University. And finally, the University of Chile designed and produced the ALMA Band 1 optics, the lens and horn, which is presently in use by the astronomical community. So thanks. Many thanks for listening, and special thanks to Professor Emeritus Jose Maza, which helped me a lot with the first part of this program.
So are there questions for Leo? I found that quite fascinating. Thank you so much. And it's amazing, the growth in students. And we're so pleased to be collaborating so greatly with you, with Chile. So I think Jim had some announcements. That concludes the session. And thank all the speakers. Let's thank them all again for a great, and I turn over the mic to Jim.
Thank you, Gordon. We're arranging now to bring out lunch. It'll be out here just momentarily. Good time for rest breaks and charge your glasses. And we will convene at 15 minutes earlier than your schedule says, just so we can be on track by the end of the day. Thank you very much.
Okay, hi everybody. This is a delight to be here. Is there a clicker? Thank you very much. So I'm privileged to talk to you today about the oldest light in the universe. But before I get started, I wanted to remark on one thing. So I'm in my second year at Duke now, and before that, I spent 14 years at Cornell. I got all of my degrees at Cornell, and I just wanted to thank CCAT and the Fred Young Submillimeter Telescope for the career advancement that has provided so many students and postdocs and faculty now. So it's been thrilling to watch the next generation of scientists cut their teeth on these instruments. And it continues to be thrilling now to build a group and watch my own students do the same. So I'll be talking about the cosmic microwave background. That's the light you see behind the CAD rendering here. And does it work? It does. So let's orient ourselves in this diagram of the entire history of the universe. I always remark on having 15 minutes to talk about the entire history of the universe. It seems a little insufficient. But our present understanding of what happened in our universe's history begins with the Big Bang. And there is this postulated theory of rapid inflation that we are eager to understand in physics today. Then the cosmic microwave background was emitted nearly 400,000 years after the Big Bang. That's what today's talk focuses on here. And after that, we see the formation of all of the structures we know and love, culminating in our planet today, where we can build exciting instruments like PrimeCam and field them on incredible new telescopes like FYST. And you heard all about PrimeCam from Mike, so I won't talk about the instrument, but I am excited to field it for this and other science goals. So when we're talking about the earliest phase of the universe, we're thinking about an incredibly hot and dense plasma. The universe was very compressed into this high energy state. So in this diagram here, we have the Big Bang to the left. That's the beginning of the universe as we know it today, or we know it. And then today we have it on the right-hand side here. And time moves from left to right. And early on, the universe was opaque to light. Photons or light particles were bouncing around inside of this dense plasma, unable to escape. And kind of like on a cloudy day, how you can't see the sun until the clouds thin out and allow light to travel freely, it was only after about 380,000 years after the Big Bang that we could finally observe light. So we call this the cosmic microwave background. We also call it the surface of last scattering. That refers to these light particles scattering for the very last time before they travel for some billions of years until they're rudely interrupted by our telescope. If you look at the cosmic microwave background, it's actually highly uniform. It's practically the same in any direction you look, and that gives us some very interesting questions that we are seeking to untangle. And one thing that points to is this period of inflation early on. And this is a black body spectrum for those of you who might be familiar with something like a hot, glowing charcoal or maybe a piece of iron that you're smelting. We know that hot things glow. And the cosmic microwave background similarly glows at a characteristic temperature of 2.7 Kelvin. So that's what you're seeing here. This is a plot of relative intensity of this ancient light as a function of wavelength in millimeters. And we have studied this now for quite some time. And CMB, that's the abbreviation for the cosmic microwave background, these surveys have focused where the cosmic microwave background is the most intense. And FYST is going to open new windows at these smaller wavelengths that will elucidate many of our exciting science goals, which I'll get into in coming slides. Now you're seeing a nod to what we actually study in the cosmic microwave background in the background of this plot, the colorful little deviations from this perfect black body. So although the cosmic microwave background is incredibly uniform from one place to another on the sky, we do see fluctuations, and that's what we study to untangle our universe's history, its components, and its evolution. One thing that's very exciting about FYST is the resolution it provides from the ground improves upon previous studies like this map from Planck. Here we see this baby picture of the universe. Again, this is the oldest observable light in the universe as it was imprinted right after the Big Bang. But we can do better in terms of resolution when we add large mirrors, like here in the Atacama. So if you add in data from the Atacama Cosmology Telescope, suddenly bright emissive point sources, like these red points you're seeing, and you can actually see some galaxy clusters in here. I could point to them with my stick, but I'm not going to do that, pop into view. And so this resolution, I'll toggle back and forth for a minute, really allows us to elucidate these exciting objects, and FYST is going to enable, like we talked about today, all of these exciting high-resolution studies in these new wavelengths. So what we've done with these measurements over time is we have written down our answer to the standard model of particle physics, our standard cosmological model. We call it lambda CDM, lambda for dark energy, which dominates our universe's composition, and CDM for cold dark matter, which follows. And the stuff that we're made of, the things the table is made of, the food you just ate, what you're seeing with your eyes, that's all visible matter. And that only comprises 5% of the entire universe, which is kind of disturbing, right? We have the standard model that tells us that we don't know 95% of the universe. So we're seeking to untangle that. But it's a great known unknown now that we've established this model and description of the universe. So the Simons Observatory is our neighbor here in these mountains. Here you can see the Simons Observatory site. And FYST is up there in Cerro Chajnantor, above the site, again at this incredible elevation that pushes above this location. But on Cerro Toco, SO is now observing, and with this observatory, we'll be targeting these larger wavelengths for unprecedented measurements of the millimeter wave sky. And because we're right next door, we're going to have access to the same sky, and combining these data sets is going to be thrilling. We're going to have an unprecedented understanding of this oldest light. So here is an image depicting why this is exciting. Because we're basically in the same place, we have complete sky overlap with the observing areas. So this white band you're seeing here that's denoted in the brackets is our wide field survey. This is going to be the area we're observing with PrimeCam on FYST, and it's going to have complete overlap with these Simons Observatory measurements, allowing us to combine data sets in a truly unprecedented manner. So here is just a nod to what our smaller wavelength coverage is going to achieve. In these images, you can see wavelengths between 1 centimeter and 0.35 millimeters, and just intuitively notice that different wavelengths of light are giving you different information about the sky. And importantly, you see those CMB baby picture fluctuations becoming completely overwhelmed by something else. These are foregrounds. We need to remove these to study the CMB and extract all of the information within it, and it's becoming increasingly important to control these as our measurements improve over time. So with our small wavelength access, we will be able to uniquely untangle these signals that are impeding our progress overall. One of these signals is polarized dust emission. This is a particular type of foreground contamination that is going to be limiting our ability to understand what happened in the earliest moments of our universe's history. So we have this inflationary period that we really think occurred. There's a lot of evidence pointing to it, but we've never seen the smoking gun of inflation. And one way FYST is going to contribute to this is characterizing these foregrounds that are going to be limiting our understanding of the signatures that tell us what happened in those earliest moments. Additionally, we get to watch the bones of the universe as they develop over time. So here you see, it's not an everlasting gobstopper. It kind of looks like an everlasting gobstopper, but this is the most massive galaxy cluster that the Atacama Cosmology Telescope measured here on the right. This is El Gordo, the fat one. And galaxy clusters are the most massive gravitationally bound structures in our universe. They live in what I keep referring to as the bones of the universe, which is large-scale structure. Matter wants to clump down at certain distance scales gravitationally towards one another, and it creates this beautiful web. And within that web, these structures form. These are clusters, as the name suggests, of many, many galaxies. And there are many open questions about how that large-scale structure evolves. For example, we would like to understand the role dark energy plays in that expansion. We're starting to constrain that. And we also can use it as a lab for fundamental particle physics, because things like neutrinos, these very light, mysterious, elusive particles, actually change the way that the universe's large-scale structure evolves over time. And so in any case, what we can do is a number of combinations of analyses that are currently flourishing in our current analysis climate, combining optical data, like you see on the left, with millimeter, and now, excitingly, submillimeter data across a wide area of sky. So I was told this would play. Will it play? No. Maybe if I click it, I don't know. It's okay, I have a plan if it doesn't play. All right. Do you have any tips or tricks? Rick to the rescue. No? Okay. That's okay. I will use my vivid description terminology. Okay, what you would see, if this were playing, would be a photon, a light particle, emitted from the cosmic microwave background, and it would undulate with its wavelength across the sky. I'll interpretively dance the cosmic microwave background. And as you can see, it's red here. It has some characteristic wavelength. But what it will do every so often, some small amount of these photons will interact with electrons that live in especially clustered down gas, like the gas in galaxy clusters. What happens is that photon gets a shift in its wavelength. And so this is called the Sinayev-Zeldovich effect, for our friends who discovered this way back a few decades ago. And this effect is uniquely important for measuring various wavelengths and untangling it from the cosmic microwave background. So this is not an ancient signal, right? This is a later time signal where the CMB photons are being changed by the matter between us and this surface of last scattering. So what you see here is that these everlasting gobstoppers of galaxy clusters change color between the different frames. And when you go from large wavelengths to smaller wavelengths, the signal becomes blue at first, and then it disappears entirely at a certain characteristic wavelength, and then it becomes suddenly an increment or an increase in temperature. So we're very interested in studying this, and because of the small wavelength coverage of FYST, we're going to get new windows into these massive objects. They're going to give us new clues as to how the universe formed and what is happening inside of these clusters, giving us new astrophysical measurements. So here you can see that illustrated in this plot. This is showing the intensity of this effect as a function of wavelength, or in this image, frequency. And notice this rainbow splitting. That's a unique signature present in some of these galaxy clusters that really has not been able to be studied, that FYST is going to give us some of the best windows possible into measuring this effect. And we also have a chance to study some signals that have never been measured before, but we think are theoretically present. That's kind of similar to this postulated theory of inflation. So you might know why the sky is blue. How many people know why the sky is blue? You know. Okay, many people know why the sky is blue. It's this thing, and so now I moved to Durham, North Carolina. The nearby city is Raleigh. It's ruined my ability to say Rayleigh. This is Rayleigh scattering, it's not Raleigh scattering. But this is an effect where the light scatters in such a way that what you observe ends up being blue. Now, an analogous effect happens where there's some atmosphere, if you want to say, after the cosmic microwave background photons have been emitted, and they scatter in a characteristic way that, again, has been theoretically predicted, but never yet observed. And the small wavelength coverage of FYST gives us a unique tool set that, again, humankind has never been able to use before to try to pry into the signature and measure it for the very first time. So in summary, and I think I did well on time, right, Nick? Yeah. So in summary, we're going to have this incredible new tool, PrimeCam, which you heard about from Mike, on FYST, that is giving us a unique wavelength coverage of our universe. We're going to be able to pick apart signatures that had previously been too highly correlated in the wavelengths we've been observing to measure this ancient light, the cosmic microwave background. And we're going to use that to understand the fundamental physics of our universe, know how it evolves over time, and also study astrophysical objects like galaxy groups and clusters to probe fundamental physics. And I'm personally thrilled to be part of the team that's going to be integrating PrimeCam coming up. So thank you all for being here, and please stay tuned.
Our next speaker is Professor Renée Hložek from the University of Toronto, and she's going to tell us about the cosmic dawn.
I had a question for Eve, but it was, what is the thing that scares you the most about the experiment? And I realize that's a very terrible question to ask as you're about to leave the stage. We can save the fears for later this evening. I wanted to echo the comments made by others. It's a real privilege to be here and to not only get to talk about the fun science that we want to do, but also to experience this generational thing. So I was a graduate student on the Atacama Cosmology Telescope, not too far away from where we're going to be tomorrow. And I now am sharing the stage with people that taught me, people that I engaged with, as a postdoc, as a student, and it's just a real honor and a privilege to be around with you and to be part of this super exciting thing. So, imagine we were all in a very exciting party. Maybe we'll do that tomorrow night. There's a lot of noise, there's a lot of sound. That's sort of how you've described that early time. The CMB photons interacting with these ionized electrons and protons. And then everybody gets tired, the universe cools down, and there is this period of the Dark Ages, right? There's a period where we know the universe was actually neutral. But of course, nobody can ever stay sad and quiet for long, and we now know we live in a universe that is mostly ionized. So we had to go from a period of the Dark Ages, stuff being very cool, calm, neutral, to the current universe. Actually answering that question of how that happened is one of the biggest remaining challenges in cosmology. How did we go from a universe that was neutral, calm, just atomic, to ionized, re-ionized, and excited? And this has been, of course, something that people have studied for many, many years, but the FYST and CCAT are the next generation of instruments that are really going to help us pin this down. So the way we think of it happening, I love these sort of illustrations of what might be happening. It's sort of the same as how a new party would get started. So you're all sitting around, but it only takes one person to start whispering to somebody else, to start energizing a conversation. Maybe you pull people around, maybe the noise, the volume increases, and eventually these small whispers grow until it's ruckus again, just as we experience whenever we come and join together. And so it's that understanding just the process that is so challenging, because until relatively recently, all we knew was that at one point it was neutral and then it was ionized. So how did we find that out? Well, Gunn and Peterson in the 60s really had this realization that because we have neutral gas, there's an incredible thing. I think one of the most exciting things to me about physics and cosmology is that a lot of it is just understanding how atoms and light interact with each other, which seems like it would only take a little while, but actually it's just been generating the careers of half the people in this room. And one of the cool things is that if you have a neutral atom, in this case, the example I've shown you is hydrogen, and you have a photon of a very specific wavelength, super specific, that hydrogen atom will absorb the energy and it'll get excited. What happens after that, of course, many other things can happen. It can give more of that light away, but in the beginning, it's absorbing the energy and it's getting excited. And so if you can map that radiation, and when that happens, you can actually see when the universe is neutral, because the neutral gas are absorbing those photons. And Gunn and Peterson, hopefully this will play, let's see. Yes, sorry, Eve. And so observations of very, very distant objects that were giving off this high radiation allowed us to probe where the neutral gas was in the universe. And in fact, at some high redshift, we noticed that there's this we call the Gunn-Peterson trough. There's a lot of absorption, and so we know the point at which reionization was over, because beyond that we see this absorption, which is great. So we know the time in which the party was fully happening, but we still don't really know how it started. We know that reionization will start because big, hot things started little whispers, make the bubbles around them. How hot were they? How big were they? How many were they? And how fast did it happen? And for a very long time, we couldn't answer those questions. The cosmic microwave background that Eve so fantastically introduced gives us a clue, because we have, now maybe this will also play, it's a little cool diagram from my colleague Wayne Hu. So because there's an anisotropy, there's a spatial variation in the CMB photons, you actually impart a little bit of polarization to the light from the electrons around the time of reionization. So the polarization we can detect just in the way that sunglasses work, but of course you all heard today about instrumentation. It's much more complicated when we're doing it on a telescope, but we can detect that there's polarization in the light. And that tells us something about reionization. It sort of tells us the sort of integral of how many conversations or how noisy it was between us and when reionization happened. Great. So we get a little bit of a clue from that. And this is a plot from the Planck telescope, which gives you some of the allowed lines. So the colored lines that you see is that integral of, like, we call it the optical depth. What is the integral of the signal until the CMB? And then the gray area is sort of the allowed band from Planck. Planck is a satellite, well, was a satellite that was measuring the cosmic microwave background from space. And really, you need those very large scale measurements of the whole sky to tell you about this reionization signal. Great. The problem is that only also really tells you when it's done. It gives you a little bit of information about how long it took, but it doesn't tell you more about the bubbliness, how the process actually happened. And through that, we can actually learn a lot more about the sources doing reionization with experiments like CCAT. So in order to do that, we need to exploit, again, the coolness of atoms. This is oxygen, so it's not exactly the line that CCAT will observe, but if any of you want to talk about atoms, we should do that all night because they're very, very exciting. But there's a very cool thing that happens in an excited state of an atom. So we think about atoms, and they have different energy levels where the electrons can be. The ground state, maybe you've heard of, there are excited levels where the electrons can be. Now, the cool thing is that atomic physics is very well understood because we know what the energy levels are of those different atoms, electron energy levels. So if you have an excited state, if you have an ionized atom, or you have an atom also in the excited state, you can actually move electrons up and down. We saw the example of the hydrogen atom absorbing a photon. And because the energy levels are very precise, it means that the radiation that is given off in that excited state is also very precise in its wavelength. So that's as if someone at the party had a code word. And if you hear this code word, you kind of know exactly what's happening. Because you now can hear the code word, you can map out these conversations that are happening. So it's almost as if, because we have the very well understood atomic physics, someone's calling me, they have the code word. Because we really understand how atoms work, it means that we have this incredible ability to measure radiation coming from all periods in the universe from these specific regions. And that's why it's so important. So the cool thing about these particular lines is they're also called forbidden lines, which kind of makes me feel like, ooh, I'm working in a very cool, exciting area that is not well understood. It just means quantum mechanically they're less probable. So instead of being forbidden, they should just be called super not probable lines, but that's much less sexy to sell. But the cool thing about these lines is because as reionization happens in the universe, there are different periods depending on how close you are to the hot thing. So for example, again in our conversation analogy, if someone's having a conversation, the closer you are to them, the more information you get, but also depending on what conversations are happening, you can learn different things. And so depending on how close you are to the source that is doing the ionizing, you get different strengths of line in different atoms. And so something like CCAT is going to tell us, in particular, about the C2. So it's going to tell us carbon, and it's going to give us physics about that gas. So why does that matter? Well, we want to know how the conversation started. That means we want to understand what are the things that are causing the reionization. How is it happening? And being able to measure that precisely will be able to tell us that. Oops. Another thing that makes this so exciting is that this intense line that is emitted by the ionizing sources, and in fact by all things along the line of sight, you can't see in different wavelengths. And so really what CCAT is going to allow us to do is to look at things with new eyes. You've heard this new window analogy. But in this diagram, you can see this is sort of the brightness of the same simulated patch of sky at a range of different frequencies. So on the very edge, you have galaxies. They look like little dots, cool but boring. So that's all matter. Then you have the galaxies that we observe. Now you'll notice there's a difference between those two panels, and that's because you can't see all the faint things. It also depends on the resolution of your telescope, so we can't always see the very, very fine structure. But what you'll also notice is, as things get fainter, they get harder to observe. When you suddenly go to making measurements at different frequencies and you can see the lines, suddenly there's so much more that we can see. And the cool thing is we can see how it evolves with redshift. So instead of just looking at line intensity at one redshift, we can actually take a snapshot at different times in the party, find out how the conversations evolved and how the universe went from this neutral state to the ionized celebrations we know today. Thanks so much. That was very effective. You stood up and I shut up. Oh, yeah. So the interpretive dance would have to be like, you could tell I'm not a pro like Eve.
Thank you, Renée. So our next speaker is Professor Manuel Aravena from the University of Diego Portales. Sorry about my pronunciation. And he's going to tell us about cosmic dawn to cosmic noon.
Yeah, well, thank you very much for having me here. So yes, well, we have heard a little bit about FYST, about submillimeter astronomy, about the early universe as well. So today I'm going to tell you a little bit about why FYST is so important for the studies of galaxy evolution. So this is a different view of the picture that we have seen in most talks today. So this is the cosmic timeline. And today, even though we're not sure exactly when the first stars started to shine, we think they started to shine at about 200 to 400 million years after the Big Bang, in an epoch called so-called cosmic dawn. After that, the galaxy growth started to pick up, and then galaxies started to evolve and had a peak of galaxy growth at about between 2 to 6 billion years after the Big Bang. And this is where we believe more than 50% of the galaxies and the stars in the universe were created. So actually FYST will be able to trace galaxy evolution for about 95% of cosmic time, of cosmic history. So this is pretty remarkable. So one of the reasons why studying galaxies and galaxy evolution is so challenging is that actually a significant portion of what we see, or what we want to see, is hidden by dust. And in this diagram, I'm showing a blue star, a young star, which is emitting a lot of course, blue and ultraviolet light. A lot of that light will encounter, typically in actively star-forming galaxies, will encounter all this dust, and a significant fraction of the blue light will be scattered. Another part of the blue light will be absorbed by the dust. However, this dust will absorb and then will re-emit part of that light in the far infrared, in the millimeter and submillimeter regimes, which is exactly what FYST can prove. So this is a picture that we have seen already, but this shows very clearly what I mean with the previous diagram. So essentially, when we look at an optical image on the top figure, we see the star like directly, what we would see if we had like eyes of 1 meter each. But then if we look at the submillimeter infrared image, we see a totally different picture. So essentially what we're seeing here is the dust glow, or the light from dust that is being emitted, and this shows us the other half of the story. So essentially, essentially what we need to understand galaxy evolution is to have both views, both the stellar light, the UV light, but also the infrared and submillimeter. So let's see an example. We just saw an example at the nearby universe here, in the modern universe in the right-hand side, but let's see an example of the early universe now at about 2 billion years after the Big Bang. So this image shows a picture, optical and submillimeter images of a galaxy cluster, J0846, in both regimes. As you can see in the optical image, you cannot really disentangle what it's there, in there. You see a bunch of galaxies, but really when you look at the submillimeter, you can actually see the galaxies that are behind. This system, it's composed of around 11 dusty galaxies that are compressed in a compact region, forming a protocluster core at 2 billion years after the Big Bang. And objects like this is something that we really want to discover and understand and study with FYST. So one of the key measurables or observables is the star formation rate when we study galaxies. So this is important because this tells us, the star formation rate tells us how fast a galaxy is growing and how fast it's building stars. So by measuring star formation rates at different epochs, we can actually reconstruct when galaxies were actively making the stars. But most importantly, it helps us to distinguish between evolutionary phases. For example, if you have a galaxy that have a high star formation rate, we will see that probably that galaxy is undergoing a starburst or an active phase of star formation. On the other hand, if you have a low star formation rate, you will think that that galaxy is shutting down the star formation and is not forming any more stars. So it's very important because it also connects to the physical drivers of galaxy evolution, so essentially mergers, environments, feedback from black holes or star formation. So FYST will be able to trace the dust obscure star formation, which is the missing part of this cosmic story. So this picture kind of compresses a little bit of our current paradigm of what we think of galaxy evolution in general. So in the bottom panel, you can see the cosmic star formation density as a function of cosmic time in the top panel and the redshift in the bottom panel. The blue curve or blue region shows us the unobscured star formation rate density of the universe, and the orange curve shows us the obscured star formation rate. So what we can see is that the star formation rate increases from early times up to a peak at about 2 billion years of the Big Bang, but it's called the cosmic noon, and then decreases steadily to the present time. The middle panel shows us the same, but in a different view. So essentially, we're seeing what fraction of obscure of star formation is due to obscure star formation and obscure star formation. So what this tells us is that dust obscure star formation is actually not necessarily a minor contribution, it's actually a dominating contribution, especially at later times. And the top panel divides the obscure star formation in different luminosity ranges. So essentially, more luminous galaxies are in the dark orange, and then less luminous galaxies in the yellow region there. So what this tells us is that at a very high rate, at the very early universe, in the first few billion years of the Big Bang, the star formation, the obscure star formation, is dominated by the most luminous galaxies, which is essentially what we can do with FYST. However, a big caveat is that, especially for the few first billion years of the Big Bang, there are huge uncertainties. So you can see here that actually it's more than an order of magnitude in these measurements. So that's exactly what we want to do with FYST, discover the early galaxies and try to make these measurements with much better precision. So the big questions we're trying to understand is, when did these dusty galaxies first appear? How much star formation was hidden from us at early times? How do we connect the first galaxies to the peak of the era of galaxy growth? And what is the role of environment in shaping galaxy evolution? So let's see a few examples of how FYST can actually discover routinely these kind of systems that so far have been the tip of the iceberg of current submillimeter surveys. So this shows the submillimeter image in the Herschel, and then the higher resolution image from ALMA. And originally, this source looked in the Herschel maps, in the submillimeter maps, looked like an extended source. But when you actually went to ALMA, you could see that it was composed by 14 different galaxies. In astronomical terms, this is a redshift 4.5. This is about 1 to 2 billion years after the Big Bang. And these kind of objects, these kind of massive objects were already forming. So FYST will find many more of these rare, dusty, rapid evolving systems through large areas of the sky. Oh, I forgot to mention that this study was led by Tim Miller, but Scott Chapman's students in Canada. So another example is detecting the first galaxies, the first dusty galaxies. And this is a study by Dominik Riechers. You've probably seen him today, of course. Was almost more than 10 years ago, but this is still one of the earliest dusty galaxies, one of the few early dusty galaxies that we have discovered. There are not so many, maybe 10 or a handful of them only. So as you can see in the submillimeter, after you have found this galaxy and then you can start to study, you can start to see whether these galaxies are in active phases and try to wonder how these galaxies obtain such amounts of dust and how the dust and the gas supply was done so early in the universe. Just to put at some context, the time it takes for our own galaxy, the Milky Way, to give only one turnaround in rotating is about 200 and something million years. And this is only 800 million years after the Big Bang. So our galaxy wouldn't have gone into 4 loops, and this galaxy was already formed after the Big Bang. So this is pretty amazing. So JWST and ALMA have been revolutionary, they have been transformational, but they're not the whole of the story. JWST is currently giving us images, very high fidelity images of the stellar components of galaxies, of the ionized gas component of galaxies, but at the same time, ALMA is also giving us a very detailed view of the images and spectroscopy of the cold gas and dust. However, both surveys cannot do what FYST can do, which is surveying large parts of the sky. So actually, all these facilities are kind of in synergy. So with FYST, we expect to do a census of hidden star formation where previous far-infrared surveys ran into confusion, meaning that previous far-infrared surveys were not able to have the angular resolution and the depth enough to actually resolve these sources at high redshift. And the current forecast shows that about 500,000, we expect to detect 500,000 dusty galaxies over 100 square degrees and around 1,000 galaxies in the first few billion years after the Big Bang. This is just by going 2 to 3 times lower luminosities than Herschel. So essentially, an important point is this synergy between JWST, ALMA, and soon ELT that will be with FYST, which all of these, once you have discovered these sources with FYST, you can actually go and disentangle the properties of these galaxies with these other facilities. So just to summarize, 3 main takeaway points. One is that much of the galaxy growth was hidden by dust, and really to observe and understand galaxy evolution, we need to look at the stellar component, but also the dusty component. JWST and ALMA are great, but they're not the whole story. We really need to go into wider areas to actually study the galaxy, identify the galaxies first, and then study them in detail. And FYST, of course, will provide this wide field census that completes the picture. Thank you very much. Well, that's a good question, because ELT is going to go into the synergies with ELT, if I could elaborate a little bit more with synergies between FYST and ELT. So ELT is at the other extreme, I would say, because currently the jump in angular resolution and sensitivity that JWST and ALMA can do is about a factor of 10 or 100, but ELT will provide another jump of 100. So probably what we will do is to try to study these identified galaxies with ALMA and JWST, but then we will make the next jump into studying even smaller and closer regions in much more detail with ELT. This is something that the other, with higher angular resolution, much more sensitivity, even though it's also a different wavelength range. Thanks. Thank you.
Thank you. Okay, I have so many things in my hands now. Great. Our next speaker is Professor Amy Stutz from the University de Concepción. I'm trying. And she's going to tell us about galactic ecology and in our Milky Way, as well as the Magellanic Clouds.
All right, well, I just have to say it's extremely humbling to be here giving this talk. You guys have done amazing work, and you can see that in all the talks we've seen so far. But anyway, time is short, so I'll cut to the chase. What is known today about star formation? So Manuel just told us some very interesting things about it. And so we could ask, you know, what do we think about this process? So many people might say that we might think about something like this external galaxy observed in carbon monoxide, the Whirlpool galaxy, which goes down to about 50 parsec scales, so that's pretty good, right? We should be thinking about small scales. Or maybe we think of this giant train wreck of colliding gas and dust, triggering many star-forming regions all over the place. Or maybe we think of the fireworks galaxy, which is just popping off in supernova, one after another. So these supernova are the explosions of massive stars. So these are excellent measures and descriptions of star formation, but they're based predominantly on metrics that are either too coarse in spatial scales or sampling the wrong time scales. So I told you about how we're sampling these supernova, so this is stellar death. So some of these metrics are sampling the timescales on which stars have not only already formed, but are already dying, right? So if we want to get at the physics of star formation, we want to go to small scales and small timescales. And we can do that in our own Milky Way. So another way of saying this is that we want to access individual sources of energy injection in these big fluffy clouds that stars are forming in. And we can do that in our Milky Way, and we can do that with FYST. So I'm going to ignore a whole bunch of astronomy and a whole bunch of details and just talk about a few aspects that I think make FYST very special in relation to star formation. So we already saw, I think it was in Frank's talk, that we have these precious atmospheric windows. And we want to ask, in the submillimeter, and we want to ask, so what can FYST do for us with its precious windows? And I'll start with the Chai instrument. So fortunately, Dominik told us everything we need to know about Chai. So again, I can cut to the chase and simplify, and all I want to talk about are two elements, carbon and oxygen. So, as was just explained to us, we get different spectral lines here of different transitions at specific energies. Some of them are from neutral carbon, and some of them are from carbon monoxide. And to first order, these transitions are tracing mass and heating budgets. That's all we really need to understand for the purposes of this talk. So what is the neutral carbon telling us about? Well, we know that it's more extended than some of our canonical tracers. So this is like a messy observer astronomy nerd picture that's hard to understand. And this is the cartoon that maybe you should be paying attention to, where the blue line is the carbon transitions, where it's excited and it permeates the whole cloud. And then the carbon monoxide is inside, and maybe the dust is even further inside. So we can get a more complete census of the material in these clouds where stars form from this additional tracer. So one message is mass depends on tracers. And not only that, but we want to know how this mass is distributed. So in terms of carbon monoxide, essentially we have a temperature tracer by measuring ever higher energy transitions in these carbon lines. So we can assess the heating budgets in the clouds. So what about PrimeCam? So PrimeCam measures polarization, which is critically important, and the take-home message here without getting into technical details that actually I don't even understand, is that this polarization traces magnetic fields. Okay? So no magnetic fields, no polarization, polarization, magnetic fields. So that's pretty cool. And here's one example, just so you don't have to take my word for it. So on the left here, we have this red blobby thing, which is this massive filament. This is an example of work from my student. And then we have an example of Sophia's measurements of polarization vectors. So this is the plane of the sky orientation of the magnetic field, if you want to get technical. But anyway, it gives us some information about magnetic field morphology. And then we can develop a model with these, anyway, I call them Van Gogh diagrams, but these kind of line integral convolution diagrams for what we think is happening with that magnetic field. So those are two observational anchor points for us, but we have to deal with the main question, which is why should we care, right? So if I reach back into the recesses of my undergrad physics classes, quite a while ago now, I remember that we have 4 fundamental forces in the universe, only 4. And the only ones that operate on the scales of interest in molecular clouds are gravity and electromagnetism, right? So when we have one tracer, we're going to be missing mass. And then with another tracer, maybe we start cooking with gas, right? And when we combine them, we get a closer approximation to the real mass in the system. So this mass contribution, I think, cannot be overemphasized, in the sense that it's like if you have an air traffic controller at the Frankfurt airport that doesn't know what time it is. This is bad news, right? So if we don't know the masses of the systems we're studying, we don't have the gravity, so we don't have a framework to understand what a fast velocity is or a slow velocity, and we can't evaluate if the magnetic fields, for example, are energetically relevant. So this is why this question of carbon is so important, and what the mass budgets are in these clouds. So in my forces slide, of course, I totally oversimplified, and there's additional phenomena that are important. So one of them that we should mention is turbulence. So this is a hand simulation by Leonardo da Vinci of a turbulence cascade in water. So you see the eddies forming. And so this guy didn't know that clouds are permeated and formed from turbulent velocity fields. But he did recognize that turbulence was a fundamental aspect of fluid dynamics. So today we know that clouds are formed from a turbulent ISM. So they have these turbulent eddies, and some of these lines that we'll have access to with FYST will trace this outer envelope that bears the imprint of cloud formation. Now, the story isn't quite that simple, because here we're observing via Doppler shift in the spectral lines the consequences of the process that we want to understand, not the process itself. Now, we're astronomers, so we're used to that, that's fine. But in this case, it bears mentioning, because there's other known processes that happen that also alter those Doppler shifted velocities, such as feedback, for example, where we have massive stars that are forming inside these clouds. They heat them and eventually destroy them via their own radiation pressure, winds, etc. So we have to be careful with our interpretation of just velocities. So FYST is then tying together these very important anchor points on our understanding of star formation by leveraging the higher resolution observations that we can get inside our own galaxy, where we can understand processes of cloud emergence to the formation of massive stars and star clusters to the ultimate cloud destruction via feedback processes. So I like to refer to this as modes of an integrated process. We have to understand this as a life cycle from cloud birth to cloud death in our own Milky Way. And with that, I'll leave you with my final slide and say thank you very much.
Thank you, Amy. Right before I stood up, excellent, 10 minutes, perfect. Any questions for Amy? Anybody want a sticker? I'm gonna keep trying. Okay, our next speaker is Doug Johnson, who is a principal research officer at the Herzberg Institute in Victoria, Canada. And Doug's gonna tell us about transients.
All right, thank you very much. It is a pleasure to be here. It's a pleasure to be speaking amongst all of the rest of the younger generation. I don't know exactly how they chose me, but maybe it's because of the time domain title. So I want to switch gears here and talk about basically a completely different axis. You've already heard from everyone about why we want to be working in the submillimeter, and I will explain that as well. I want to talk about why we want to tackle what is a new area of astronomy in many ways, although I'll mention how it's got a history, and that is the time domain. And that is adding, from the frequency range all the way up now to looking at how do things vary in time. And as I said, I look forward to a feast of variability with this nice new telescope that we're getting. Okay, so time is crucial for astronomy. We already heard about how the CMB is, from Eve, giving us information that is billions of years old. We heard about how its galaxies, their cycle is hundreds of millions of years. We heard from Amy about, the star formation process, which can be millions of years. So if I'm going to talk about, if I'm interested in astronomy, I'm interested in how things evolve. They're not static. That's one of the most important things to consider. I'm a star formation person, so I'm interested in sort of 100,000 years to maybe 50 million years, sort of the early stages of a planet, of extrasolar systems. But for the purposes of this talk, I'm not going to bore you about very long timescales. I want to think about things that happen on human timescales. And so I'm going to start with, this is an extrasolar extrasolar system, and you're watching planets go around over the course of about 7 years of observing. And I want to connect that back to what, the ancients did when they called them planets, right? They were the wandering stars. And then what, Galileo and Kepler and Newton, and how we got to physics by noting that things were moving in the sky and that we could connect that to what gravity was on the Earth. Similarly, the other type of things that we'll often look for are explosive events like flares on the sun. And that's also a connection back to the past, because it was the notion of sunspots that commented again about the fact that the sky was not perfect, and the sky was maybe a little bit more like the ground, and we were interconnected. And then finally, I want to point out that there's another set of objects. This is a simulation, not a real observation, but there's another type of object which suddenly appears in the sky. Every once in a while, something will go boom. And if we wait just a few more seconds, boom. So the variable sky is really important to us and has historically been very important to us. But until recently, the variable sky was something that we did in the optical. We started by doing it with our eyes, and we moved to optical telescopes, partly because of the ubiquity of optical telescopes, but also because it's been hard to do in the submillimeter. And I'll get to that at the end, because FYST is designed to be able to do time monitoring. And so what I wanted to point out here is that when we look at an object that is varying in time, and here's an example where you've got, a donor star dropping onto a disk that ends up creating a nice jet and working surfaces in the jet, you want to observe this at multiple wavelengths for the reasons we heard earlier, that there's different physics at the different wavelengths. You can approach the problem differently by using all of the different wavelengths that you have for you. Closer to my heart, you want to get to the submillimeter because if you're interested in how a star forms with the disk around it, one of the reasons you're interested in that disk is that's where planets are going to form. And what comes along with planets are complex organic molecules that might lead to life. And we know that as the star changes in brightness, which is one of the things that happens, and I'll show that later on, as the star changes in brightness, it changes the heating in the disk, which changes the properties of the disk, which leads to evaporation of material and puts organic materials back into the gas phase to end up on planets. And this can be observed primarily in the submillimeter. So I thought it wouldn't be appropriate if I didn't give you a little bit of history of my own. This is my world records of the shortest observation I've seen of variability that I've been involved in, which was watching something vary on 30-minute timescales. I'll come back to that one at the end. But I also want to point out, FYST may give us a legacy. Undoubtedly, it will give us a legacy. This is the longest observing that I've done. It goes back over 100 years to photographic plates taken at Harvard of a source called EX loop that they already knew was variable on the Harvard plates, but they didn't know what to do with it. We now call this an eruptive protostar. I'll talk a little bit more about protostars later, but every once in a while it does a burp, and it basically gulps a little bit more mass onto the star, and we've been able to therefore watch it for over 100 years to see how it's varying on those timescales. And hopefully FYST will be the start of that, right? You gotta start somewhere of giving you the time domain data. Okay, so what will FYST actually give us? We're gonna be doing two different types of observing with FYST. One of those is monitoring. That's what I've been doing a lot of. We're gonna go to sources that we think already are interesting, and we're gonna try to go back to them on a regular basis, and we're just gonna monitor them to see what is happening, like monitoring your heartbeat, like they were doing for us with our pressure, right? And what are the types of things that you might look for here? You might look for dust production in a supernova. You've watched the supernova form, and now over time you want to see whether or not it's sweeping up dust, whether it's creating dust, because dust is really important. Another thing you might be looking at is an active galactic nuclei. That's one of those black holes like they were mentioning at the center of our galaxy. And they vary on all sorts of timescales, and we can watch them vary. In fact, we've already started doing that with previous telescopes, but not uniformly like we'll be able to do with FYST. There's compact sources, there's comets when there's a comet going through the solar system, and then my favorite, protostar variability. So let me just take a couple of seconds to talk about that. When you form a star, you have a local clump of gas that basically has the mass of the star in it. And that clump of gas is held together by gravity, and it's held up by thermal pressure. It's held up by the fact that there's pressure holding it back. It collapses from the inside, and the material starts to fall to the center at free fall, basically just like dropping a ball. If it were for nothing else, that would go straight to the center, but there's always angular momentum, there's always spin. So the material doesn't make it to the center, it makes it to a disk, a rotating disk. And in fact, history, we figured out about how the solar system formed through this, because if you actually ask the question, where is the mass in the solar system? It's all in the sun. Where is all the spin in the solar system? It's all out in Jupiter. Jupiter got the spin, it's the leftover spin of the disk that ends up in Jupiter. So you're building the star by building a disk and then building the star. And getting the material through the disk is tricky. We don't know how the material moves through the disk. Got lots of theories, lots of good ideas, but we don't know how the material moves through the disk. What we do know, it does get to the star, and as it goes to the star, that last mile it drops down, not quite a mile, that last little bit that it drops down is deep in the potential well, gives off a lot of energy, and it is luminous. It's very bright. But you've got this envelope around you, and much like Eve was saying earlier from the CMB, you can't see because it's optically thick. You can't see to the optical. So instead what we do is we watch the temperature of that envelope vary in response to the heating that's going on at the star. So what I like to say is I'm going to use FYST to look at these envelopes around protostars and use them as temperature gauges, as thermometers, to see what's happening at the center. And what we want to do is we want to watch the variability in the material falling onto the star so that we can do protostellar disk seismology. right? We use seismology on the Earth to understand the properties of the Earth. We use seismology on the sun to understand the properties of the sun. And we want to use seismology on protostars to understand what's going on in the disk to hopefully break this uncertainty about how the material moves through the disk. So can we do it? We've already been doing this at the JCMT in Hawaii, but FYST is going to be much better because we're going to have a much better telescope designed for this kind of work. And this is an image over 8 years. This is a light curve over 8 years, watching a source vary in brightness. And you can see that it's got a long-term variation of about 8 years and a short-term variation on top of that of about 2 years. This is what it looks like with ALMA. ALMA's great to see down to the disk. It's a very interesting disk. The disk is warped. Something's happened to that disk. We're probing it right now on these shorter time scales of 8 years and 2 years, and I just want you to think, what might be years in a disk? Well, if you have a sun like ours, 1 year is the orbit at the Earth. So whether or not that's the type of location we're looking at isn't clear yet, because we don't know what the driving feature is, but it could be, and in fact we argued in another system that it may actually be driven by a planet in its own solar system that is causing the variability. Okay, what we really want to do though is get to diagrams like this. I wouldn't be a research scientist if I didn't try to show you a diagram that has very interesting axes. So this is the time scale of the event getting out to centuries, and on the axis, the y-axis, you're seeing how strong it is. And so we have these very rare big bursts, and we have this very common low amplitude stuff. And what we really want to understand, another of the things we want to understand is, are they separate? Are they individual type events? Or is this just a continuum? Is there some type of organized criticality, self-organized criticality? So I'll jump through the short-term stuff. This is the other thing we'll be doing by watching as we observe every day. We will watch to see if anything has changed dramatically in the sky. And I just want to show you one example of flaring. And this is from our observing before again. On the right, on the upper left panel, that was an observation on the 20th of November, 2016. 6 days later, there was a bright object in the sky, and a few weeks later, the object had disappeared. Things don't do that, usually. In fact, over 30 minutes, if you broke this observation down, the object decayed 50% in brightness in half an hour. Thermal objects don't do that if they're big enough to be bright enough. This is a non-thermal event. It was the most powerful flare from a young disk. And if a flare like that happened in a place where there were planets forming and the like, it would do an awful lot to the chemistry that Amy was talking about earlier. Okay, so I just want to end with one last thing, which is this doesn't come for free. We've been trying it at other telescopes, and it's really hard to do. But thankfully, FYST has been uniquely designed to allow us the time domain. It has access to a large fraction of the sky at a given time. It has large focal plane arrays to allow you to do fast scanning. We'll have multiple frequencies that we can use at the same time. We can control for systematics, which is what these guys know I'm arguing with them about all of the time. We've got phenomenal dynamic range, and we will get real-time results rather than what I just showed you on a flare where we went back and had to look at archival data, so we couldn't look at it the day after. And if you want to do the short-term monitoring, it's even more important to have telescope agility and the like. So I want to thank the hard work that everyone's done. I want to thank those who helped us get the telescope. That means the money to actually be able to build it and the brains to know how to build it. And I want to say that I really am looking forward to a feast of variability. Thank you. I'll answer questions for Pisco Sours tomorrow night. That's right. Who's next?
Great. Our next speaker is Professor Abigail Kreitz from Cornell. She's going to tell us about the collaboration.
All right, thank you very much. I'm here to kind of give a little bit of a logistical view of how we work together as a collaboration, but also talk about what it means to be a collaboration and kind of who is doing all of this work. And one of the things that we have heard from Martha and others today is that we like each other and we share a common purpose for making this science happen. So everyone in this room, as well as our students and postdocs back at our institutions, are all coming together to make this happen. And we've thought about the generations as well. There's another generation that is back at our institutions working on all of these problems, cracking up PrimeCam, doing all of these things. And so I'm going to talk both about those people and also kind of what we're going to make that will be lasting. And then Nick will pick up on kind of the legacy of FYST. So, as you all know, the science would not be done without all the amazing scientists and engineers around the world and the people that have supported us and funded us. And this is a picture of our collaboration. It's back in 2023, I think, because we've had some logistical problems traveling, but we had many online meetings and pod meetings since then. But this is what we looked like in 2003, so you can see us at Cornell. And this is just a little bit of a silly chart. No, it's a very important chart. But this is what tells us how the collaboration and the board of directors and the entire CCAT Observatory organization works together. But our committee that I am the chair of, the collaboration committee, works to kind of take all of the pieces and weave things together so that we can write papers, give talks, and record what we've been doing on FYST for the future. And in addition to just doing publications, presentations, as you all know, we're very interested in sharing our science with the broader community. So we're interested in overseeing and promoting education and outreach for FYST. So one of the very exciting things about FYST and CCAT is that we have just been leading up to this moment where we're all going to see the inauguration of FYST. But there have been many publications in journals and conference proceedings talking about the development of FYST, all the way from the initial designs up to what we're doing now in detector testing and theory that tells us what we're going to be able to discover with this set of instruments in this telescope. And so you can already just see, if you look at your favorite place to go to find papers, you can see that we're already writing an incredible amount of papers about the things that have happened in the development phase, and we'll keep doing that for years to come. We also give presentations about FYST and CCAT at conferences, and you can just see a few pictures of people's slides and also students talking about their work on FYST and CCAT. And these are also some other pictures of our younger generation, I guess, us young faculty as well as students and postdocs that are going out and talking to people about the science that we'll do with FYST, bringing students from an even younger generation into the lab to work with us on this work. So I think that one thing that I want to highlight is that this project is carried out by the young scientists that are back at our institutions under our guidance. But the really fascinating and exciting thing about FYST is that this subfield of submillimeter astronomy is one of the last places that students can get incredible hands-on experience from the very design of an instrument to building the instrument, to deploying it, and then ultimately writing papers about the science. And that's much more rare these days than it was even when I started in this field. And I think that FYST is incredibly important, and it's incredibly important that we keep doing this work, because that is where we're going to train the next generation of astrophysicists and physicists in instrumentation so that we can continue to do science like this. And so we'll someday be the ones building a new instrument and showing our next generation of young colleagues how we're going to progress in our scientific studies. So thank you, and I think Nick will pick up from here.
Great, thank you, Abby. I think I'm not going to bother to ask for questions. I'm just going to continue on. Martha asked me to talk a little bit about the legacy value of what we're going to be doing with FYST. And I thought I'd just start, you guys have seen this many times, so I thought I'd talk about sort of the multi-croic nature of what we're doing. And so here's a picture of fruit. I think it's apt because we're talking about FYST. And this is a monochrome picture of fruit. Now, I would ask you, but I don't think you'll respond, if you could tell me what each of these fruit are just by looking at it in monochrome. It's very difficult to do, right? And there's an advantage to seeing things in multiple colors in the visible light. As you can see here, now you can start to pick things out, see what's important, see what's ripe, right? And so with FYST, with PrimeCam, with Chai, we're going to be doing that over the next decade, actually, with our unique submillimeter window into the universe. So here we are. You've seen this already. Martha showed this. We may have taught the same course before and used this image before. Hint. But so here we are in FYST, right in the submillimeter here. But there's a huge wavelength range, right, of places we observe the sky in. And so what's key here is with FYST, we are, as you've heard, going to be making observations at it's going to be the best depth, so the furthest we've seen, at the highest resolution that anybody has done yet, over a large area of the sky. And this is going to be really impactful if we want to start putting things together. A lot of modern astronomy is not done at one wavelength, as you've heard. It's done across many wavelengths. And so our wavelength here is essential to many of the science goals you've heard about already today. One of them that you haven't heard about, and this will be my only real science slide, is we're going to be studying magnetic fields in star-forming regions, similar to what Amy talked about. And this is our Galpol survey. So they're going to be surveying lots of individual star-forming regions, looking at the role of magnetic fields, looking at the properties of dust, looking at the role of turbulence, all things that Amy mentioned as well. And this is just to demonstrate how deep we're going to be going with FYST and how much better we are than the current observations out there. So here's Planck, a Planck satellite on your left, and here's what FYST is going to be doing on the right. And basically, redder is better. Redder means we're going to be observing at much higher depth, lower noise levels than Planck at much higher resolution. You'll see that Planck doesn't have any of these 1 arc-minute resolution areas, whereas we have a majority of our galaxy. This is the galactic plane here, as well as well out into things like the northern polar spur. So this is going to be exquisite for studying the properties of star-forming regions, as well as, so we have this multichroic image or picture. If we start combining it with other data sets, as Amy pointed out, we'll also have a lot of spectral information. So we'll be able to learn about the chemical properties of these regions as well. What molecules are there, how fast they're moving, things like that. So this is going to be key. And a lot of the science that's going to be done with this legacy data set we haven't even talked about yet, because there'll be other surveys coming online that will help add. And CCAT and the data from FYST will be essential in sort of teasing out those new science goals that we haven't even thought about, new science problems. Maybe we'll find interesting objects, as we heard about this morning. So this is really not only a data set for us now, but it's going to be a data set going decades into the future. So with that, I think that's the last slide. That's the last slide. I won't be taking questions. And before we wrap up, I was told we had to finish fast enough, and I think we did. But I wanted to say thank you to the folks who helped put this together before I hand it over to Jim, who's going to tell us what to do. So first, let's thank Martha. I know Martha's been working very hard on this because I've heard we're on the same floor at Cornell. So I hear about it every day. So thank you, Martha. Thank you to Jill in the back. And thank you to Talia, who's our organizer in Chile. And lastly, I wanted to thank Jim. Where's Jim? Where is Jim? We can wait for Jim. Can somebody get Jim? Jim is also speaking next. We finished too early, so thank you to Jim for organizing this. Now, before I hand the mic over to Jim, I was told that today's also a very special day. It's also Jim's birthday.
I worked hard to make it my birthday.
And so I guess we're singing? We're going to sing. 1, 2, 3. Happy birthday to you. Happy birthday to you. Happy birthday, dear Jim. Happy birthday to you.
Thank you.
Speech. We got a question. Oh, okay.
Thank you, everybody. 62, and in this audience, that's not saying much. Okay, my slides up? There we go. I'm going to tell you about tomorrow. So today this is just the practical ending of today and setting up for success tomorrow. You are 5 groups of approximately 20 people going to a very, very high site tomorrow. You know that because you had your blood pressure taken, or most of you. Thank you. You've passed at a very high rate. I really appreciate it. It makes our life tomorrow much easier. As Dr. Cooper told you, have fun. You're going to enjoy it. Many of you have been to these areas before. Some of you haven't. Those of you who have been there before and are old hat to wearing oxygen and things, you're going to help everybody. If you're looking around and you see somebody looking a bit intimidated, step in, help them out. Everybody also needs to look out for everybody. Oh, Dr. Cooper hasn't presented yet. Nope. Well, then I was called out of my meeting a little too early. Let me introduce you to Dr. Thomas Cooper. Okay. Dr. Cooper is quite eminent in the world of high altitude and extreme altitude medicine. He is a physician, and particularly high mountain climbing and all of those kinds of things. People do. Who knows Ivan Lopez at ALMA? Most of you, certainly most of your astronomers. Ivan, genuflex and kneels to Dr. Cooper. The standards that we use, that ALMA use, he is greatly influenced. All of that we're doing today and the processes that we do, and even the Chilean law that defines labor law, that defines how we protect people at these altitudes. So I will come back up in a few minutes. Let's bring up Dr. Cooper's slides, please. He has a presentation. I read it. It's quite good. It has 2 movies in it. And I will come back and tell you more about the tour process for tomorrow. Thank you. Dr. Cooper.
Hello, everybody. Good afternoon. Honorable Young. It's not only a push for astronomy, it's also a big push for health and safety for workers at extreme altitude in extreme environments. This is one of my specialties at Aachen Technical University, and this is why Professor Stutz asked me to join the team, and so I'm the responsible physician for occupational medicine of the European astronomers, engineers, and technicians. And it's great to be a member of this team. I don't want to train you as high-altitude physicians or as high-altitude specialists, but I want to give you some important advice how to feel good tomorrow at this high-altitude site. First take-home message, hypoxia is an absolute normal thing of your daily life. Press your fingernail, you see it becomes pale. Pale means there's no perfusion. No perfusion means there's no oxygen. Actually, my feet are hypoxic. Guess which part of your body is hypoxic right now? Okay, let's have a look. Oxygen at high altitude, we have the same percentage, but there's less pressure. And we need the pressure to bring the oxygen where it's needed at the cells, the fingers, in the muscles, and wherever. And because the pressure is lower,
less oxygen will reach the site where it's used, and less oxygen there means there's less energy. And this is what you feel. You are already at 2,400 meters now. I think only a few people of you have realized that you have lost here at least 10 to 15% of your exercise capacity. And that will be even more up there. Look, if you go higher, the pressure goes down. Some data from Europe, Innsbruck is a town in Austria, Rudolf is out in the mountain, La Paz. You will be a little bit higher than Mont Blanc, and somewhere between Mont Blanc and Aconcagua tomorrow morning. The body, fortunately, is able to counterbalance that. Some data are very old and still the same, and it's fair to make the reference to the guys who made the first paper of it, because all the others just copied. This is glacier and the balloon ascent, and you see the pulse rate increase with altitude. You will feel that tomorrow a bit. You will have around about 15%, 20% higher pulse rate at altitude. It's normal. As I told you, the energy will be less, the exercise capacity. Until 1,500 meters, which is lower than we are here now, your body doesn't even realize that you are at altitude. But then you have a loss of 10 to 15% of your exercise capacity per 1,000 additional meters of altitude. And again, you will be somewhere here. This is the line, historical interesting. The Incas realized that permanent acclimatization is only possible at up to 5,300 meters. Look, shall we start this? This is a decrease of exercise capacity. You see doctors ascending to a medical training in the European Alps. And keep in mind the speed of how they are walking now. And this is at Denali in Alaska, 5,200 meters. And the guy in front, they are at the limit of the exercise capacity, what they can do. And the guy in front, Ulf Gieseler, one of the most experienced German expedition doctors, at the age of 63 was able to run a marathon in 3 hours 30. This is, now they are up there, and even higher at Cho'oyo, up 8 to 10 breaths per step. You must do just to continue to walk. Fortunately, it's not so hard for you tomorrow, you will see. But take home message 1, don't rush if there's not a need to rush. Slow down at altitude. Balance and coordination is decreasing at altitude. It starts already here, and there's no good data in science, but we assume that the risk of stumbling and falling in acute hypoxia is higher. And you can see that this person on the left side is well acclimatized, and the coordination is quite good. This is at the side of the telescope. You will be there tomorrow morning. And the other person is acute exposed to high altitude, and you see the difference in coordination quite well. So please keep in mind that you are a little bit limited, and focus on your steps. Where are you going? Temperature. According to ICAO atmosphere, you have a decrease of 0.6 degrees centigrade per 100 meters of altitude gain. It will be much colder up there. Even it's fine here. I calculated that for 20 degrees centigrade at San Pedro, you will have less than minus 10 degrees centigrade at the telescope. The problem, there's an additional problem, Sippel and Parshley, they had a boring time in World War II in Antarctica, but they had frostbite. And then they calculated this well-known table. So when we say we have the minus 13 degree centigrade up at the telescope, plus wind, potential wind, you are easily at -30. This is the temperature you feel on unprotected skin. And unprotected skin may freeze within 2 or 3 minutes within the yellow range and freeze in 30 seconds in the red range. So please take warm clothes along, but don't take this warm clothes on here. When you are sweating and the clothes are wet, they will not protect you against the cold. And the outer layer should be windproof because there will be some wind above there. Radiation, per altitude, reflection if there's snow, all these factors significantly increase the exposure. So we have, if I look around, 2 different skin types here. I told that North American pale type. Please be very careful, it's skin type 1 and 2. And we have the South American skin types here. They are a little bit more protected by nature. But however, please use sunscreen where covering of your skin is not suitable. And the Italian or South American skin type should use at least sun protection factor 15, probably more, and or 13, probably more. But don't forget your lips. They are very exposed. There's one thing you should not expect: altitude disease. You may, after a while, you may have mild headache. But altitude disease has a latency of at least 4, normally more hours. This is a normal acute mountain sickness. You will never die by acute mountain sickness, but you don't feel well. The high altitude pulmonary edema, HAPE, or high altitude cerebral edema, you may die by these diseases, but you are too short exposed, and the first symptoms of this disease will not occur before 12 hours of exposure, and then you are back down in San Pedro and we have the dinner. If you should have headache, please never ever use aspirin at high altitude. Just 1 pill of aspirin in hypoxia may cause stomach bleeding. And so prefer paracetamol or ibuprofen. But the most important take-home message is have fun up there. Thank you so much.
Thank you, Dr. Cooper. Questions for Dr. Cooper? For many of you, part of what he touched on, or why for the first day you go up, if you were part of my staff, you could only be up there 4 hours the first day. You can't be there more than 12 hours in a day. All that ties into the data and everything that we've learned so far about these skills. So thank you very much for your contributions to this science and for educating us on it today. Thank you, Doctor. Okay, so now this is when I'm supposed to be here. Of course. Well, while we're waiting for batteries or to figure out how I broke something in 30 seconds, you are 5 groups of 20 people. And the logistics involved with moving you all safely up and down the mountain are quite complex. Hopefully, it will look simple to you tomorrow. But please be flexible. Please be flexible. Thank you. One of the things that you need to be aware of is this really helps us help all of you tomorrow. Your name's on the front of it. Hopefully, you have a smiley face on the back of your name tag. If you do not have a smiley face on the back of your name tag, either you've told us you do not intend to go to the summit tomorrow with us, or you have not been medically screened yet. If you want to go to the summit tomorrow and have not yet been medically screened, please go through our health check stations before you leave today. There is a chance for you to be rechecked tomorrow at Alma, but we have limited time and space to do rechecks. So if you need one, and we'll take care of it, but please, if you've not had your initial screening today, please do it on your way out. On the bus, there's a press bus, a bus A, and a bus B. They will be labeled. The buses will be at Palpana Street. You have a QR code that tells you where Palpana Street is. Also, Google Maps and Waze will get you there absolutely reliably. Those of you in the Nyara, you will be brought there by the Nyara. I need you there by 10 minutes to 9 a.m. tomorrow. The buses need to leave for Alma at 9 a.m. And unless your name is Fred Young Jr., the buses are not going to wait for you. Okay. When you get on the bus, we'll get you to Alma, we'll get you through the gate, we'll get you to the Operational Support Facility, the OSF at Alma, where we will do the inauguration ceremony tomorrow. At the conclusion of the inauguration ceremony, I will come back up again and issue final guidance and answer final questions, and then we're going to be off in groups. Group A1 and I should have said this earlier, Group A1 and Group A2, you are both on bus A. So tomorrow at 10 till 9, find the A bus, get on the A bus. B1, B2, you're on the B bus. Press and press support, you're on the press bus. Now, getting to Alma, you can actually ride any of the 3 buses, but it would help you if you start in the morning on your assigned bus. You'll feel more comfortable, and we'll have an accounting. Could I ask Jürgen Stutzky to please stand up, and Frank Bertoldi? They are your B-bus captains, your hosts, right? Can I have Dominik and Norm Murray stand up? These are your hosts on the A bus. They will be with your group through the rest of it. And Robert Zeman, he is the press bus person. Now again, in the morning you can get on any of the buses, but it would help you to be on the appropriate bus and make eye contact with your bus host. Okay, after the inauguration tomorrow, the first bus to leave will be the press bus. About 15 minutes after the press bus will be the A bus, and the B bus will stay at the Alma Support Facility for about an hour. We have tours to give you. We have some other interesting things to keep you occupied. About 1 hour later, you'll head out. When you're getting on that bus, when you get back on that bus, in your seat, you will have, I broke it again? You will find a backpack bag in your seat. Inside the backpack bag is a Type D oxygen cylinder, a continuous flow regulator, and a nose cannula. And we'll go through that, each of those. This is what, there's your oxygen valve, and you're going to see it's on 0, and you're going to see it's empty. And you're going to go, bus captain, I've got an empty cylinder. No, you don't. The valve's not open yet. We don't need you using your oxygen at this point. Next slide. When instructed, when you are asked by your bus captain, you will open the valve counterclockwise. Sometimes the valve is hard to move. If you need help, the person next to you or the bus captain will get it open for you. You're still going to leave the regulator on 0. Next slide. And lo and behold, you'll see you have a full tank of oxygen. If your valve is now open and this doesn't go to green, you need to let your bus captain know. We do have extra bottles of oxygen on each bus in case there's equipment failure. Don't worry, we got you covered. Next slide. This is your nose cannula. It's a plastic tube with these two protrusions on it. This is what's going to deliver the oxygen into your nose. And they're angled. This is dramatic, but they're angled up. You want the up angle going up towards the top of your head. It works better that way. It'll work either way, but it works better if they're angled up. Next slide. That's a beautiful picture of what you look like when it's on right. Some people wear the back of it down their back. Other people wear it under their chin, and you cinch it up so that everything stays nicely in place, you know, over the ears and through the nose. If you need help, there are plenty of people on all the buses who've done this before. They'll show you how. And don't be embarrassed. Next slide. Now you're ready. You've got your bag. You're set up to go. Remember, when you're breathing properly, your belly comes out. That's my story, and I'm sticking to it. Next slide. Now, again, when instructed, you turn that 0, you turn this knob from 0 to 1. To 1. Oxygen is now flowing. You have a continuous flow regulator. What that means is when you open that, turn that dial, oxygen goes. There are different kinds of regulators. I'm not going to cover that now. This one, oxygen is on or it is off. For those of you who have a lot of experience at altitude or going to ALMA or going to these things, if you know that your setting is lower than a 1 or a higher than a 1, go to the setting you know. If this is your first time, start at 1. Next slide. You will, at some point on your ride, pretty quickly, be asked to stick your finger like you did today in a pulse oximeter. A pulse oximeter tells you two things: your oxygen level in your blood and your pulse. We want your number, your pulse number, your oxygen level, your blood oxygen level to be 93 or better through the trip. If you start going below 93, breathe deeply. Remember to breathe through your nose. A lot of people, when you're out of breath, you start to pant. The cannula's in your nose. You need to, right? A deep breath through your nose, and this number's going to come up within seconds. It's going to be really quick. We want you stable above 93. If you are not above a 93, then we're going to turn your 1 to a 2. Right? We have plenty of ways. We're going to get you settled. Okay? As far as pulse, your pulse is going to be higher tomorrow, some because it's just exciting and some because, as Dr. Cooper said, your pulse is going to be higher as you're at higher altitude. It's normal. Of course, if you're running above 100 and stuff, let your bus captain know, okay? But we don't have any pulse triggers. If you feel like your pulse is racing, though, let somebody know, right? Next slide. You will be asked, somebody sitting next to you, somebody you know, you need a safety buddy. That person is somebody who should stay with you at the whole time of the summit. So pick somebody that you think is kind of going to meander at about your same speed and stay with you. Look out for each other, right? So have a safety buddy. You'll be asked to do that. And those people you should kind of enjoy the tour experience together. However, everybody needs to look out for everybody. So if you see somebody zoning out, that kind of 40-meter, what's going on thing, touch them on the shoulder and ask if they're okay. Ask if they're okay. Stick with each other. If you feel dizzy, if you feel unwell at any time, there are chairs up there. Just sit down, breathe in deep through your nose. It will likely clear up in a matter of seconds. And if it doesn't, we will be wearing those bright orange construction vests. All you need to do is signal us. We will come immediately and ask how we can help, and likely we'll turn up your oxygen level, but it's a matter of breathing in calmly through your nose. This is normal. So those of you who are a little intimidated by this, I know there are a few, just stay calm. As Dr. Cooper said, calm and slow and steady, you'll be fine. We've taken visitors up before. You're going to be fine. All right. Back one. If somebody, there are safety people all over the summit and on the buses. There will at times, somebody will hand you that pulse oximeter. If somebody hands you a pulse oximeter, it means please put it on your finger. It's not oh, no, I don't need that. I feel fine. If somebody is bringing you a pulse oximeter, they want to know that you're fine. And because sometimes, in some people, you could be in the low 80s and not realize it. Okay? Well, geez, I'm really magical. That was really my last key slide, subject to your questions. But it is quite, you're going to get about 35 minutes at the summit, about 35 minutes. It's kind of short, but we need to do that to get everybody through and then back for the celebration. All of you that have achieved the smiley face and those who are still about to achieve the smiley face, we hope, that is not licensed to now you can have all the caffeine you want and all the alcohol you want tonight, okay? Moderation, if any, definite moderation, okay? The whole point of this is for tomorrow. And just because you passed, you know, we need it all, we need you in the state tomorrow. The transportation people that are going to take you up to the summit, you'll be taking a bus out to the service area. We'll explain what a service area is. Taking you to the summit on four-wheel drive trucks. Those trucks are going to deliver you right in front of the Fred Young Submillimeter telescope. You'll exit the vehicles, you'll gather in front. The press people will take official happy snap photos and tell you where to be. And people like Ronan Higgins and others at the summit will tell you what you're looking at and answer your questions. Nominally, you'll get 15-ish minutes in front of the telescope, and then we'll invite you to the side. And the staff have created a beautiful overlook area for you to see down on the service area, down on Alma, all the surrounding views. They did a fantastic job. I hope you will agree. That is also, just beside that viewing area, is where you will be picked up for the trip back down to the service area to get on a bus that will take you back to Popana Street, therefore to your hotel so you can get ready for the celebration. The celebration is where you can have all the caffeine and alcohol you want, and I'm even buying most of it. So wait until the celebration. It's going to be a great day. You're going to do great. Most of you know that. Those of you who are a little intimidated, you're going to be fine. Do you have any questions for me at this point? Press will leave first so that they're ready to receive the rest. The A group will split into two. They start as a full A bus, and half of the group will get off at the AOS technical building and take a short tour while the A1 group goes straight to the summit. I'm limited to bringing people up at 21 at a time. I tried to make the groups as cohesive as far as affinities and travel partners and stuff as I could. It's not a perfect way. You know, one group isn't necessarily more important than another. Some of you are in the B group because I know I'm going to have to test you at Alma, and the A bus is going to have to leave before your medical checks are complete. So there's a lot of thinking in that. But A1 will go first, A2 will go second, B1, and then the last group is B2. And A1, A2, you get on the A bus. We'll take care of it from there. And B1, B2 on the B bus. And again, it should be seamless. There may be a bus might arrive at the service area and the vehicles aren't ready to take you to the summit. There could be a 5-minute wait there. That's okay. You know, the timing is pretty rehearsed. So.
How long does it take to get from OSF to the top?
Okay, from the OSF to the service area takes approximately 1 hour even. A full hour to drive. No, it takes an hour to get from the OSF to the service area. It takes 15 to 17 minutes to get from the service area to the summit. So you're going to get to the service area on the bus. Then we're going to transition to four-wheel drive trucks, 3 people to a truck, pick the first empty truck, you know, and your travel buddy, and then they will go up in a convoy and set you off at the base of the telescope. Do your telescope time, do your beautiful viewing and take selfies time. You'll get back in those four-wheel drive vehicles to go back down, where there'll be another group waiting to get in, and you'll be waiting to get in the bus. The bus will go to the hotel, and the other group will continue up and take their summit tours. So it's there are 5 groups that are going up, 5 groups coming down, all 28, 21 to a group.
They don't go back to OSF, they go to the hotel.
Correct. So once you come off the summit, we're taking you home so that you can get ready for the party. The other thing I should say now, and I hope I repeat tomorrow, you will not necessarily, and highly likely, not going home on the same bus that you get taken to the mountain on. The way that, because we have an odd number of groups, don't worry about it. Just make sure you have all your possessions with you. We will have people who will sweep through the buses at the end of the day, and if you left something, we'll be the lost and found. But hopefully, you'll remember to take things with you. We also have box lunches. There will be box lunches in the seats of the bus, so you will have water and a light snack like apple and yogurt type things because we're traveling kind of over the lunch period. And it's always good to keep your energy up, but we don't want to feed you a big meal. That's not helpful. Okay? Hans? You should always have water, but we will be providing water. There will be water on each bus. There will be water at the summit. We also have an executive bathroom at the summit. So the buses have a latrine, a toilet. Alma has, the AOS Technical Meeting has, and we have them at the summit as well. So never fear. We got you covered. And other questions? Think about it, and you'll get a chance to ask me again tomorrow before we start the big adventure. It's going to be exciting. You've seen a lot, and even you've seen very, very current pictures. So, but seeing it with your own eye, it's still very, very special. And I look forward to hosting you at the summit tomorrow.